Inside, it's kind of warm. So, one of your collaborators gave a talk recently at UMD.
Yeah, Tabu.
Yeah. So, did he talk about this work, or is something? I mean, you may not remember. But...
I don't know exactly what was in this talk, but
okay.
I think this was part of.
Yeah, I think he probably talked about this.
How's that? I'm already behind.
Huh?
I'm already behind.
I think that clock is a bit.
Yeah.
But like a minute.
That's true.
No, no. Like I didn't have it enough.
That reply. I was foggy on that.
All right. Thank you, everybody. Thank you, everybody, for waking up early. And for our first talk, we're pleased to have Csaba talking about dynamical work mass generation by QCD-like. Thank you so much. It's great to be back. Hopefully, there will be more workshops like this. So I'm going to be talking about the work that we just finished with my collaborator, Turin Roy. So he's at the Tata Institute in Mumbai. Max was a postdoc at Cornell. Now he's a postdoc at Stanford, and Harry is a joint postdoc between Kias and Cornell. All right, so I'm going to just quickly remind you about, this funny, sometimes forgotten idea about maybe having the upward mass vanishing and not having the strong CT problem. Then I will try to explain to you how the dynamical quark masses are actually encoded in chiral perturbation theory. And so what are the quantities that we would need to calculate in order to be able to say what the dynamically generated quark mass is. And then I'm going to give you a very quick review on the kind of theories where this calculation is actually possible. So it starts out with a supersymmetric version of QCD, and then we add of supersymmetry breaking. In particular, here we add it using anomaly mediation, and we get a theory that in some ways resembles QCD. Of course, it's not QCD, but for example, this calculation is possible. So we'll show you how to get the results in this theory, and see how large the contributions to the upward mass are. All right, very good. So we heard a lot about the strong CP problem and axions, etc. What I want to emphasize is that, of course, strong CP problem is related to QCD, and understanding the dynamics of QCD is one of the last frontiers within the standard model. For example, we don't understand the mechanism of confinement and many of these things. So that's, of course, still a big unsolved problem. And, the strong CP problem is somewhat related to that. So as we heard yesterday from many speakers, we have this topological term. And it breaks CP, except if theta is equal to 0, pi. And the physical version of this parameter fits into the EDM of neutron and tells you that the bar appears. Very good. So what are the type of solutions of the strong CP problem that we are usually considering? Well, we heard a lot about axions. Yes, essentially, we make theta to be a very light and deeply interacting field and make sure that it actually relaxes to 0. So that's the axion solution. Then there's another interesting direction to go, which is called the Nelson bar solution, where you start out with a theory where CP is actually an exact symmetry, but it's spontaneously broken. Okay? And then the main part of the model building is to make sure that, of course, we have two sources of CP violation in the standard model. We have one is the strong CP problem. We want to be very small. Again, we have the usual CP phases in the CPM matrix, which are not small. And so how to sort of, maintain, how to start out with a theory where CP is break it, but not reintroduce theta and reintroduce. So that's the game there. And it's an interesting direction, but that's not where we are going to go. And then, of course, there's a third solution that people are usually, ignoring nowadays, which would be the simplest solution. Of course, as we know, if you had an exactly massless chiral fermion, there would be an exactly anomalous U1A symmetry. Yes, that would, in this case, if the upward mass was 0, would just rotate the upward mass, and that would just make the theta angle unphysical. It wouldn't show up anywhere, and there wouldn't be a strong CP. Okay. Now, of course, the problem with this approach is that if you look at the pion masses, MAP doesn't appear to be 0. Okay. And of course, I will talk a lot more about this. Now, already back in the 80s, Kaplan and Manohar realized that actually, the situation is a little more complicated than that, because there are dynamical effects that will shift the upward mass. So that means that there are actually additive contributions to the upward mass so the renormalization of the upward mass is not multiplicative. So you could actually start in a theory where the fundamental upward mass is 0. Yeah? So you can have, for example, the fundamental Ishikawa couplings vanish. Okay. Yet a dynamical contribution to the upward mass that could possibly be sizable. Yes. And this, whether or not this theory solves the strong CP problem actually depends on whether it's the fundamental Yukawa couplings that vanish. That's because if those were 0, yes, those would remain 0, so that there would still be an actually underlying chiral symmetry that you could use to rotate away the theta. So the most well-known example which is usually quoted is, just look at QCD instantons. Okay, so let's say you look at QCD with 3 flavors. And so you look at an instanton contribution, and there would be a fermionic 0 mode for both the left-handed and the right-handed fermion, and then you could go ahead and close up the down and the strange legs just with some mass insertions. Okay, and then clearly, once we close up these legs, yes, this tooth vertex would actually look like an upward mass. Okay. So, and clearly you can see that this would actually be the most important for the first generation, yes? Because if you try to do this, for example, if you did start with MAP equals 0, yes, we would get a non-zero contribution to the upward mass, but if you try to do the same for the other generation, you wouldn't be able to close up the upward. So the expectation is that the effect will be most important for the first generation. Now, okay, that's really nice. There is, of course, a little bit of a problem, yes. You can try to go back to this vertex, to this tooth operator, yes, and try to look at the contribution of the small instantons, which are calculable. That's great. You can do the calculation, but because these instantons are small instantons, they will be exponentially suppressed. Now, you can ask, okay, how about the large instantons? Yes, well, those are uncalculable. Yes. So we don't really have a very clear idea, what the answer to this problem is. Okay, so instead, people are trying to do, of course, lattice calculations, and which does suggest that maybe the underlying upward is non-zero. But again, it's very hard, A, to do the simulation, and B, to extract the result. There's many of the simulations that people did, they are very precise on the lattice, but then they were always assuming multiplicative renormalizations and MS bar scheme, so that's not quite the right approach. And I'm not really an expert on this, so I'm not 100% sure what the status is. Some lattice people will swear to you that, oh, it's completely excluded, that MAP should be 0. But, other people are telling me, well, this is a really hard thing. So anyways, the other story, as I will explain to you, is that you can look at the Cairo perturbation theory, and you can just fit the coefficients of the Cairo perturbation theory to experiments. And I will explain to you exactly, this is the route we are going to be going. But, yes.
May I ask you a question?
Yeah.
Let's assume lattice convince us that the mass of the upward is 0.
Right.
But you just told you that there is a calculable part, dynamical.
Well, so the question is, can they tell you what the underlying upward mass is? So everybody agrees that it's what we call, and I will explain to you what I call the dynamic, it's non-zero, yes? You just look at the Pion mass formula, it's non-zero, yes? Question is, what does it come from? Yes? Does it come from completely the dynamical effects, or is it a mixture of the two? Is it yeah? So
That's not lattice, just put them up 0 and try to fit all the spectrum. If you can manage, that's it. But you cannot manage. So this is why they have, I don't know, they claim 5 sigma deviation from MAP equal to 0.
Right.
So
yeah, again, the question is
more,
what are they really extracting?
From the Apicava or?
Yeah, the input is the Apicava in the spot.
And the hierarchy is the kernel algebra mass parameter, but that is the fundamental mass parameter, right? So we're talking.
Anyway, I'm just going to show you what our calculation can. Everybody can, argue on the lattice. I'm not going to make any sides on that. What I do want to say is that Cairo perturbation theory actually wants to push you in the direction of larger dynamical contributions, but they say that, well, because of the lattice, we are imposing some priors, and then it's there. Anyway, but again, all I'm going to try to tell you is that there is a theory where we can calculate this, and I'm just going to show you what the result there is. Okay. And so we are going to be looking at the QCD-like theory and try to see what the corrections there are. Okay, so first of all, how do I get the upward mass in Cairo perturbation theory? So again, the important point is that these corrections are contained in normal Cairo perturbation theory. So let's see, what is the quantity that we will need to get the upward corrections. Okay, so the leading order Cairo Lagrangian is of course the thing that everybody is in love with. Yes, so the just the kinetic terms plus the Quark mass term, linear used as a spurion. Yes, so U is the usual Goldstone-Boson matrix, and F0 is the leading order pion decay constant. Chi is essentially the Quark mass up to this condensator factor. Okay, so this determines the pion masses. The gamma Kubo mass formula, pion scattering, but the dynamical quark mass, as you saw before from this instanton diagram, the expectation is that it will be something that is proportional, at least if you think of it as that instanton correction that is proportional to a product of the quark masses. So that's not contained in this Lagrange. Yes, you need to go to one higher order in Cairo perturbation theory to be able to extract that. So you do the second order Cairo perturbation theory. So you have 2 powers of the quark masses, or 4 derivatives, or 1 quark mass and 2 derivatives. That's how the next order Cairo perturbation theory is defined. Yes, and then you have here a complete set of operators. Yes, so you see this is like the square of the term that you looked at before, or you see they are here. These 6, 7, 8. Those are the ones that contain 2 powers of the quark masses. again, chi is essentially the quark.
It's a determinant term, right?
So we'll get to that. We'll get to that. So that's an important question. Yes. Exactly. So there's another operator here. Yes. So this would be the one that you would want to write directly down as the one that contributes to the instanton. So I like to use this cofactor, which is I don't know if people know what the cofactor is. It's sort of, it's essentially the inverse matrix multiplied by the determinant, and the reason why that's sort of the relevant thing, that's sort of the subdeterminant. The way when you calculate the inverse of a matrix. And so that's the operator that you would directly write down. Yes, so you see the cofactor for the up quark, it would be m down times m straight. So that's an operator that's again also allowed by all the symmetries. Yes. But it turns out that it's actually not independent. It's already contained in these other operators that is written down in the previous page. And okay, if you want to see it, this is a lot of fun matrix algebra. Why this is not independent? Yes. So there's something called the Cayley-Hamilton theorem, yes, which is telling you that the determinant, well, what it actually strictly tells you is that every matrix satisfies its own characteristic polynomial. Yes. So if you do that, if you expand the characteristic polynomial, one term is just going to be the determinant of the matrix, and the rest is going to be powers of traces. Yes? And now you substitute into that equation the actual matrix. You get, for example, for 3 by 3 matrices, you get an equation like this. So it tells you that the determinant is proportional to all these other matrices. And now, if you want to get the cofactor, you can just multiply it with the inverse. Yes, that will tell you that the cofactor is going to be just a combination of all these other matrices. So that's this what is called the Kaplan-Manohar identity. Yes, so you go ahead and you apply this for the term that you would have written naively for the instanton. Yes, and then you get this particular relation. Okay, so that will tell you that that operator that Matthias wanted me to write down. Yes, so that is already a linear combination of these other operators. Okay, so you shouldn't. And of course, why didn't we write this? Yes, because Leifelder and Gasser made up this basis well before we thought about dynamical up quark, etc. So we are just sticking to what the chiral population theory equals. Now, another really important consequence is that the physics is invariant. The low energy physics, the chiral Lagrangian, is completely invariant under a shift. Yes. So exactly what the up quark mass is from the low energy Lagrangian, yes, is actually not well determined. Yes, there is an arbitrary shift here. Yes, so you can see this chi was essentially the quark mass matrix. Yes, and you can shift it by an arbitrary coefficient here, and you can move this around within the chiral Lagrangian. And for example, one way to do it is you can remove the instanton generated terms. Yes.
You could also use that to set them up equal 0, right?
Yes, exactly. So you could do that, yes. Or the way we are going to use it is we are going to set it to all the corrections, all the higher order corrections to the pion masses. Okay, that's another way to say it. Okay, so in this gauge, so we say that this is like a gauge choice for this Kaplan-Manohar identity. Yes, this is what we are going to call the dynamical up quark. Okay, which is just saying essentially just more or less just take the naive relation for the up quark, for the pion mass, yes, the one without the corrections, and call this the dynamical quark mass. Okay, so
is there a reason you're calling this a gauge, or that you think of this as a gauge redundancy?
Yeah, I mean it's a redundancy.
It's a redundancy.
It's a redundancy of the physics.
Yeah,
so,
but
in that sense.
In that sense, okay.
Yeah. Sorry. So then the question is, okay, so then how do I actually determine, this up quark mass? So really to make a connection with what we are interested in, yes, what we need to do is we need to match the chiral Lagrangian to There's some issue with the connection here. This. I unplugged the power. Okay, I plugged in the power so that it doesn't do it. All right, very good. So yeah, so you need to make a connection to the UV, yes. So we are going to start then from a UV theory where the up and the down quark masses are actually given by the Yukawa couplings, yes, and then calculate in this gauge also what the pion mass is. So now we are going to get corrections from these higher order terms in the chiral Lagrangian, yes, and then again, just for the heck of it, assume that the fundamental up quark mass is 0. Yes, of course you can do it with non-zero as well, then you get a shift. Yes, but that's what we did here. Yes, and then you can get these dynamical up quark to down quark masses in terms of these operators in chiral perturbation. Okay, so now the story is, okay, let's just go ahead and get a theory where we can actually do this calculation. So as you know, of course, the supersymmetry gives powerful additional constraints on strong dynamics, and in the mid-90s, led by Seiberg and many others, they were able to nail down the structure of supersymmetric QCD using all these beautiful techniques, holomorphic, Luft anomaly mentioned, etc. Now the thing is that the phases of supersymmetric QCD actually don't look very much like the phases of ordinary QCD. And so depending on what the number of flavors is, you get a very bizarre set of phases, and some of them resemble a little bit QCD, but most of them don't resemble it at all. Yes. Now, of course, the thing is that this is the exactly supersymmetric theory, and once you add supersymmetry breaking, actually, all of these phases kind of collapse into QCD-like phases. So, for example, this phase here where you had a runaway vacuum, it actually becomes completely QCD-like when you add a little bit of supersymmetry breaking. These theories here, all of them have QCD-like vacuum. Okay, so this one resembles much more the phase diagram than what we are actually interested in. And we were using in particular a form of soft supersymmetry breaking that we call anomaly mediation. And the exact details are not super important for us. Maybe the connection is not good here. Not my computer. The reason why we are using this particular form of calculating the soft supersymmetry breaking terms is because when you use anomaly mediation, it gives you a UV insensitive prescription for calculating the soft breaking terms. So it's a really nice way to be able to understand how to go through the strong dynamics. If you added a SUSY breaking terms in the UV, ask the question, what is the effect of that on the not sure. Let me try unplugging. It gives it tells you how to go through the strong dynamics and get what the soft breaking terms in the strongly coupled theory actually are. Yes. And of course, there was Alex and Ricardo who gave us a nice, simplest way of getting these effects. Essentially, they said that look, all you need to do is just find out what all the scale violating terms in the theory are. Yes, and And so you use this Lyell compensator, and they just show up through this coupling here. That you essentially have to calculate, all the terms that are not scaling variant, and those will give you soft SUSY breaking. In particular, if you have renormalization group running, so you have non-vanishing data functions, you're going to get the genome masses, you're going to get soft breaking terms, A terms, etc., that are proportional to all the objects that are scaling violently. Okay, now the other interesting thing is there's also a tree-level term. Yeah? So if there is a term in the superpotential that is not dimension 3, that will actually give you another contribution. Yeah? So if this vanishes for dimension 3 superpotential, but not in general, and this actually turned out to play a major role in many of these theories. And so we did go through this, and I'm not going to tell you all the dynamics of this thing. What we are actually doing here is, again, take some of these results, in particular 3-flavor QCD, and we'll focus on the case either where the number of flavors, the number of colors is bigger than n, or when the number of flavors is equal to the number of colors. Yes, the one we are most interested in is f equals n equals 3, yes, but you can also take f equals 3 and n bigger than that. Okay, so we looked at both of those. We assume that we have the dynamical scale, SUSY breaking is smaller than that, and that's bigger than all the quark masses. Okay, so you just go ahead, and again, at this point, it's more or less there's a worked out procedure of how to get these effective Lagrangians, and in particular, so here we have the expression for the scalar potential. And the number of flavors is less than the number of colors. You start out with what is called the ADS superpotential, and the canonical Kähler potential projected onto the low energy degrees of freedom, which are going to be the meson fields in this case. But for f equals n, and in particular 3 in our case, you're going to get what is called the quantum modified constraint. And here there will be a little bit of non-calculable effects, because we don't exactly know what the Kähler potential for these dynamical degrees of freedom are. We know what the effective superpotential is. We know what the degrees of freedom are, but there are these uncalculable coefficients here, and those are actually going to show up in the expression for the dynamical upward mass. Okay, so we have the effective Lagrangian, yes. So that contains the chiral Lagrangian of here, yes. But so the only thing that we had to do for this project, so that's what took a few weeks, is to make sure that we actually match this effective theory to the form of the chiral Lagrangian. In particular, the effective Lagrangian is written in terms of these meson fields, which is like the QQ bar bound states, yes, and those are going to contain the usual ion matrix. But on top of it, it will also contain radial modes that are going to become heavy when supersymmetry is broken. So what you really have to do carefully is make sure that you're carefully integrating out the radial modes. And actually all the effects, all the higher order terms in the chiral Lagrangian that you're interested in are going to be coming from integrating out these radial modes from the theory. Okay, so these are the radial modes. So they are part of our Lagrangian that I have written over here. Yes, they are part because they are all written in terms of m. And then what you need to do is you need to carefully separate the Goldstone directions from the radial directions and then integrate that. So to leading order, yes, so first order in quark mass, these guys get a bath, yes, the radial directions, and that is what is going to determine the pion decay constant and the quark condensate. Yes, so this is what you get to leading order, and then at this order they are not mixing. So at this order, you could just set them to 0, yes. But at the next order, there will be the fluctuations of this radial mode is actually going to be mixing with the Goldstone directions, yes. So then you have to carefully integrate it out and make sure that that those are the terms that are going to give you the contribution to the chiral Lagrangian. Okay, so that's what we did. We identified all the mixing terms. So this is what they are mixing together. And after that, you are going to get all these coefficients in your chiral Lagrangian. Okay, so that's sort of our result. Yes, so this is telling you, okay, so most of these operators, these higher order terms, are actually non-zero. In this theory, they can be calculated. Yes, we did only a 3-level calculation. Yes, within the effective theory, the effective theories are weakly coupled. Yes, so there, the loop effects are going to be suppressed by 1/16 pi squared factors. For the case when when n is greater than f, we could do a large n expansion and see how it scales with n. Okay, so it turns out that for L3 to L8, we are going to get the expected large n scaling. We are getting the expected large n scaling the people from large n. Doing these two, we are not matching, but the large n scaling. But the thing is that in usual kind of perturbation theory, these terms are usually coming from the exchange of spin 1 particles and so vector mesons, and we don't have those. Okay, so now remember that our actual expression for the dynamical quark mass was, just calculated in terms of these coefficients that that we have over here. So L6 and L4 are what matter. Yes. Okay. So here are the expressions that we get in general. Yes. So for example, it's very simple when f equals n equals 3. So that's the case that we are most interested in. There's just a strange quark mass over the SUSY breaking scale. Okay, and this alpha is again this order 1 coefficient, this uncalculable order 1 coefficient. So as long as m strange over m is not so small, yes, this could be sizable. Okay, so this is also the contribution for when n is large. Okay, so it does go to 0 as n goes to infinity, so that's expected. But when n is not infinite, then actually, these things are pretty sizable. Okay. Now, strictly speaking, that's all we can say. So, in principle, I should finish my talk here. Yes, that's all what. And Steve is nodding for some other reason. Yes, so strictly speaking, we get no information in QCD because our calculation is only valid when m is much smaller than m. Yes. Now, I could close my eyes and dream and just take the naive extrapolation that I actually take m to be of order lambda, yes. Again, at least the effective theories are self-consistent. They seem to be matching. There's no obvious reason within the effective theory not to do it, except that your calculation wasn't valid, yes. So in that case, you are going to get some numerical answers that, for f equals n equals 3 is actually pretty big, and it is kind of in the ballpark that you would have wanted. When f is less than n, you are actually getting a much smaller contribution, and you are not completely shocked about that, is that because f is less than n, it's actually a weakly coupled theory. So that's the ADS superpotential, and the dynamics of that is really very un-QCD-like. Okay, for f equals n, the theory actually resembles mostly like most QCD. Yes, the global symmetry is actually broken without SUSY breaking, and so we would say that this is probably the closest in terms of capturing the mechanism. But of course, none of them is QCD, and our calculation is only valid in the and is much smaller. Okay, what is the mechanism for non-perturbative quark mass generation? For f equals n minus 1 and n, it's presumably instantons. But because it's a scalar potential, it's very hard to actually draw an instanton diagram, so we don't have the actual, we can't say, okay, it's this diagram. Very good. So, softly broken SUSY is a very nice lab for studying, all kinds of weird effects in QCD that we have small handles on understanding. AMSB is a good way to do this because it's UV insensitive and also produces QCD-like phases. Interesting question that we were examining here is, how big is the dynamical upward mass generation in these theories? We can do it in parallel perturbation theory, go to second order. And within these theories, it's actually pretty sizable for f equals n. And, in this theory, if you took it seriously, again, you probably shouldn't, but, could account for all of that. All right, thanks.
So in this theory, you should also have an axion, right, which would be the eta prime, right? Because
but it's massive.
So you can check the mass of this eta prime. It's near lambda, is that right?
No. Well, actually, at f equals n equals 3, it is of the order of lambda. For the other cases, it is given by SUSY, by the SUSY breakings.
So it can actually be lower than
it could
less.
be lower. Right. So that was another paper that actually I think 2 years ago, oh, you were the SUSY.
Oh, that's
I probably give out the H.
Okay.
That's the potential there.
Okay. Yes.
So we're working this one.
Okay, so thanks for the great talk. So it is known that mass renormalization by instanton is known to renormalize only the real part, not the phase part. That was one very important mechanism how masses of Quark solution can actually solve the Strong-Stick problem without turning on the data parameter. Presumably in your calculation, complex phases are encoded in this alpha beta unknown coefficients.
No, alpha and beta are real, I think.
Oh, you think
because
they're real?
that's a scale, that's scalar potential.
Okay, then my question could be whether in your calculation, at least you can say that all this renormalization effect or dynamical generation of the mass only turns on the real part, or
good question. We just said it everything for real. Okay, so we'll check.
okay.
In the f equals 3 case, the ratio that as you approach m equal to lambda, you get to this 0.4 or 0.5. What's the scaling with m over lambda for this coefficient?
Well, I mean, it didn't really depend on.
No, what I meant, well,
it didn't really depend on numbers.
Depend on lambda.
I mean, there was, so this one was about, we were just assuming that.
No, I guess what I was trying to understand is whether you could approach instead of taking.
This is the result.
Yeah.
Doesn't have a lambda. It's just that you're assuming that you are supposed to be in the regime when m is much smaller than lambda and ms is much smaller than m. Yes. So you could try to lift both of them to their numerical values. The ratio you can hold fixed, yes. So the question is, do you still trust this number? This is just one number essentially, yes. But you still trust it. Well, I don't really, but again, it's fun to play around with the idea. Yes, you.
So in small instanton calculation is deficient because it's only valid when there is exponential suppression. Your calculation is also calculable while m is much smaller than lambda, right? So is it in any sense, would be lambda being e to the minus a pi squared over g squared, is it qualitatively less than that exponential suppression? Saying m over lambda is much smaller than 1 is analogous to exponential suppression.
Yes. Well, I mean, it could be, why is it exponential?
Well, it's just different way of expressing the same measure.
Exponential.
Yeah, but that exponential is inside of definition of lambda.
Again, I mean, you are capturing here the dynamics, yes. I think all the dynamics, it's like, they are all the stuff that is uncalculable. That is captured here, yes. But you just have a limit for, how far you can go away from the SUSY. I mean, if you are asking, did I answer the question? Obviously not for QCD, obviously not, yes. But I think it is going from a different direction. So I think it is capturing some of the effects that I couldn't capture in QCD. I think for this theory, I am capturing.
I agree that it's a different direction. I'm just kind of.
If you're asking,
is there a measure? Do I come closer to an answer?
This way versus that way, why do I care?
No. I'm asking, do I come closer to the answer this way? It's a different direction. I agree.
Again, I think I'm capturing some of the corrections that you cannot calculate. If traditional instanton methods you capture here, but there's another, another limitation.
But hard because lately with this question, you have to believe that the small m is close to lambda.
Right. So
in the instanton, you have to believe. I can also believe that the weakly coupled instanton are more or less good. Okay, that's also you get an answer. So in what sense is better than because you have to believe in some limit that you.
So if you're asking about QCD, yes, it's not it. I gave you a theory. There, I can actually calculate it. Give me another theory where you can do this calculation.
We calculate in the limit where m is smaller than lambda.
Right.
And the instanton can be calculated in the limit the coupling is not strong.
No, I think I understood. You're saying that in instanton, I can calculate for small instantons, but that's not all versus in your theory.
In my theory, there is a limit where I can calculate the whole thing as a, for QCD, there's, you don't have a number. You don't have a prediction. Here, yes, Rachel, so it's what I'm waiting for.
This is a question I've been wondering about this program. So you're doing everything in the nonlinear sigma model or non-linearly realized chiral symmetry, right? If you want to ever take M to the confinement scale or even lift it above the confinement scale, which may be the ultimate initiative.
There will be all these other modes. That's why, you really should take this with the lifting it, is
Yeah, but can I ask a specific question about a lot of the implications are raising these operators to weird powers. So it seems like you can't restore chiral symmetry. Like these theories, if you were to replace the linear sigma model with a linear sigma model, right? These operators are raised to n minus f, f minus n type powers. And are you concerned that if you put the sigma field in, it can't take a 0f? Because that's an ill-defined point in the theory. So maybe these theories can't restore chiral symmetry.
Can't restore chiral symmetry.
Because they're always it's only well-defined when the symmetry is not clearly realized.
I'm sorry, no.
Yeah.
Restore chiral symmetry a large temperature or?
So if you have a nonlinear sigma model versus a linear sigma model, right? In the linear sigma model, you would also have determinant, right? And everything is well-defined in the linear sigma model. I mean, you have confinement.
I mean, this is an effective theory. Again, this is a low energy effective theory.
Yes.
At lambda, there are many other degrees of freedom. Yes. I mean, again, you really should not be, talking about physics at lambda. Yes.
Yeah, I was just curious because, in QCD, you can write down a linear sigma model which restores chiral symmetry. You probably shouldn't trust it because you have strong dynamics at the chiral symmetry restoration scale. But at least, the sigma field taking a 0f is well defined. I'm a little worried in this theory that it's not at all.
Again, I mean, this is an effective theory.
Yeah.
This is already a low energy effective theory. So,
yeah.
Assuming,
Okay, I think to cut things off, we should probably move on.
Okay, next speaker is Harigaya, who's going to talk about kinetic, acoustic,
misalignment, and Baryon.
Hello, so I'm Keisuke Harigaya. So today I'd like to talk about the written book, Axion and Baryon asymmetry. That spontaneous broken continent symmetry plays important role in beyond the standard model. For example, Keitetic symmetry can solve the strong CD problem. Deadpoint symmetry and its breaking changes in the neutral mass pair. And flavor symmetry can explain the flavor error. Those theories predict the lambda goes on bottom, with essentially the angular direction of the symmetry. Whose coupling is controlled by the symmetry rings decay. I feeder and interchange. We further explicitly break those UN symmetry as a case for the feature symmetry. Those numbers was not non-zero mass and become shoot numbers bottom. I call those five to just action, whether or not it's a QC action or action like what's interesting. So here's a summary of what I'd like to discuss today. So rotational action field in the field space in the R reverse and create a matter and thermodynamic symmetry. So that rotation also produces action dark matter through the two mechanisms, acoustic and misalignment mechanism. Action couplings predict to be larger than the prediction of the standard misalignment. So toward the end of the talk, you see the picture like this. X-axis is action mass, y-axis is the action photon coupling, assuming human symmetry of the electromagnetic anomaly. This green line is the prediction of the theory where both dark matter and the Baryon symmetry is produced by the dynamics I would like to discuss, namely the action rotation. So here's the actual outlines. I first introduce the axion rotation and how it can create a direction. So then discuss how then the rotation also produces dark matter and you fix them already. Okay, let's start from the first topic. So axion rotation just determines axion field that rotate like this. That's super simple. So this state has a non-zero angular momentum or non-zero Dyon charge. It is simply given by the angular velocity times just a real square. It's really angular momentum in the field states. So then, so how can we consider such a rotation? How can we justify such dynamics in the early universe? But we can just follow the idea from the upright time mechanism that was originally proposed for the rotating superparts two and slip. So for this, not only the dynamics of angular direction, but also consider the dynamics of radial direction that I call R. So let's imagine that the radial direction is misaligned from the minimum. So namely, let's assume a large initial field value that's radial direction. But you can easily expect if the mass is smaller than the Hartree expansion rate in the it's much larger than minimum value here. So for such high field values, so higher order terms in the potential can be effective. In particular, some of them will break the Dyon symmetry explicitly. So in fact, such terms are expected to present if the Pizzakin symmetry is understood accidental symmetry, like violation of the Baryon number by dimension 6 operators in the standard model. And there are a bunch of such models. So then, because this break Dyon symmetry explicitly, so this gives the potential gradient to the angular direction and induce angular motion like this. So this is after the mechanism. After the initiation rotation, radius decreases rapidly by the expansion inverse, and higher polar potential becomes ineffective. Then this complex field continues to rotate with inertial motion, conserving the angular momentum up to the effect of the cosmic expansion.
Do we have any model or dynamic understanding how you might achieve that initial condition?
I mean, as long as the mass is smaller than the hyperscale Darwin equation, there's no reason that it should be at the small field value. Rather, we expect large initial value.
But you're not taking Axion as inflaton here, just make sure.
No. Okay. But it's like we assume the misalignment action.
Okay.
Yeah. Now, if we want to do dynamic, we can just add the negative happiness mass to ensure that large field value dynamic. So then this is just the affect time mechanism. But just like in affect time mechanism, this mechanism can also create the Baryon symmetry difference in the following way. So the state has a non-zero Dyon charge, it's like a Dyon Pizzakin charge. So once this field coupled to standard model via the QCD-like or potentially beyond the standard model interaction, this Dyon charge can be transferred into Baryon symmetry. This is we call the axiogenesis, just an analogy with a left genesis. You first create a left line symmetry and convert it into Baryon symmetry via Higgs spiral process. So there are several possibilities, but what I consider the minimum is just use the Baryon number violation by weak interaction. So let's just a couple actions to standard model field, like a coupling to gluon or weak boson or just fermion current. So then through that interaction, Dyon charge is first transferred into higher asymmetry of the standard particles, like the excess of left-hand particles are right-hand particles, without creating Baryon asymmetry. But since this higher charge asymmetry generically has a weak anomaly, so this charge can be also converted into Baryon asymmetry. If we use the standard model process, the transfer process effect before the LQ phase transition, where Higgs foreign process is effect. and the Baryon symmetry to reach the chemical equilibrium value. Then we can easily compute the resultant Baryon symmetry using thermodynamics, namely just the balance of chemical potential. The chemical potential, the rotation is just roughly energy density divided by charge density. So that's chemical potential. So we just as slide as angular velocity of this particle, this field. And the Baryon number is in equilibrium with this, which means the chemical potential baryon should be also as large as angular velocity. So then using thermodynamics, you find a Baryon symmetry as large as angular velocity times temperature squared. So this process is frozen upon the electric symmetry breaking, below which Higgs from process in our exponential suppress. Then we can just evaluate the baryon number densities, normalized by the entropy density cancel the effect of the Higgs expansion in the following way. That angular velocity temperature squared divided by entropy density at the electric expansion. So baryon number is given by a function of U1 charge, also divided by the entropy density, and the ratio between electric phase transition temperature and axion decay. You can just extend this to more generic scenario with other baryon number or electron vibration from the beyond stuff, where you can just convert U1 charge into higher charge and convert higher charge into baryon number through, for example, minor neutral mass or R parity vibration with supersymmetry. Standard model. In this way, you can make connection between the axion physics and other beyond the standard. So there are some literature on this direction, but I just want to go into direction today. Yet I assume it's a minimal scenario that you try the standard process. So that's how we can produce the Baryon symmetry from the axion process. Now let's make connection with the axion dark matter. As you know, Axion is a good dark matter candidate because its mass is light and it's weakly coupled in the limit where the decay constant is sufficiently large. It is naturally long range. So the canonical frequently consider the production mechanism for the Axion dark matter is a misalignment mechanism, where so the axion is displaced from the minima by some amount, and the axion being oscillation at a later time. And this oscillation behaves as axion of dark matter. So there, we assume that the initial angular velocity is zero. So what's happening here is we use the potential energy of the axion to create the axion dark matter things. So that's the misalignment. But in this scenario we consider where we have axion rotation that corresponds to non-kinetic energy. So we have this potential energy plus a kinetic energy as a potential source of axion dark matter. So by just utilizing this, somehow converting this initial energy into axion dark matter density, so we can enhance the axion dark matter density. So far, two sources of this axion dark matter production is identified. One is the kinetic misalignment mechanism, where, as we will see, the express U1 symmetry breaking by the master or potential term plays important role. That I will discuss first. Recently, another mechanism was identified, which I call acoustic misalignment mechanism. Here, production of the axion occurs while U1 symmetry is still a good symmetry. So axion mass is, in our universe, where axion mass is still negligible. So let's first start from this kinetic misalignment mechanism, which is slightly simple and easier to understand. So in the typical parameter space, the production axion in the kinetic misalignment mechanism occurs through so-called axion fragmentation. To see that, let's consider just equation motion axion taking account there's a non-zero axion potential, which I take to be just cosine potential of Steve. And just expand the axion field around a rotating background with just some fluctuation. And let's just look at the equation motion fluctuation at the linear level in the momentum space. It just looks like this. The time, second derivative with respect to time and gradient time, and the time coming from the potential energy that depend on this axion factor of U axis. This is, you can see this is the equation motion of the oscillator with the oscillating frequency. And we know what's going to happen, the parametric.
Sorry, can I check one thing? Is that analysis valid only if the velocity timescale is slower than the whatever Axion dynamical scale?
Axion then.
In other words, you're doing perturbation.
Velocity should be the analysis I just result represent is varied when the angular velocity is larger than the action mass.
No, I'm checking. So there is a changing background, time varying background, and then you are doing perturbation theory with respect to that. I'm just asking whether you can only look at the Axion dynamics in the time scale, which is much shorter than time scale for the rotation itself.
Why?
I'm just checking whether, if not, do you actually have a valid perturbation theory set up?
I don't understand your question.
So you're looking at, there's a theta itself is time changing, right? And then you're looking at the perturbation on top of that.
Yes.
If this is much faster than whatever the time scale, sorry?
As I see, the time scale oscillator is actually comparable to the velocity. I'm just analyzing the classical equation motion.
And then I'm checking the validity of the classical analysis.
I don't understand why it's violated when the velocity is too large. As long as the velocity is much smaller than the dynamical scale action, the dynamical scale QCD, the QCD will just self-adjust itself. So we can actually use this vacuum configuration.
Okay, so you're claiming that this analysis is valid even if time scale for the velocity is much shorter than Axion dynamic scale. That's your claim. Just check.
Yes.
Okay.
Good. Let's move on. So as you and I expect, we have a resonance at the natural frequency of this rotation. So namely, the just angular velocity. You can actually just look at the equation motion of final resonance path at this point. Then what happens is this axion zero mode will create the axion fluctuation at this frequency. And this zero mode will fragment into axion fluctuation. So then we can estimate the axion number density roughly in the following way. We can define the axion kinetic energy by the energy of each axion quantum. So then it's just given by angular velocity times the radius square. It's nothing but as large as the original U1 charge. So in this mechanism, axion number density is as large as U1 charge density. And this is quite predictable as you know. So in this mechanism, as I told you, we can enhance axion number density in comparison with the misalignment mechanism that predicts the axion parameter space here. Okay. Yeah. So then in the orange shaded region with the label KMM, so the observed diagonal density can be explained by this kinetic misalignment mechanism with the axion fragmentation here, orange shaded region. In particular, for the QC axion, you can populate the axion dark matter even if the decay constant is much smaller than the 10 to 11 to 10 to 12. So this might be good news for those looking for axion dark matter at the high mass range. Furthermore, let's assume that the variation universe is created by the axion rotation and the weak spiral process. Then we can make even sharper prediction. And the parameter space flux into a single line, this green line. So again, the prediction for the axion photon calculation, assuming the U1 symmetry has pictured the electromagnetic anomaly, is much larger than the prediction of the conventional misalignment mechanism or the prediction of the QCD-like action. It will be a good experimental target. So before those experiments reach the canonical QCD-like. So instead of just probing the origin of the understanding the dark matter and a strong CP program, so those experiments can probe the origin of dark matter and vibration. So now let's just discuss the second mechanism, which I call acoustic misalignment mechanism. So in this mechanism, photon modes of rotation produced from cosmic perturbation, and this photon later becomes action. What is photon? So we are not talking about just vacuum dynamics, but the state with non-zero energy or angular momentum. So with this rotating background, symmetry breaking pattern is slightly modified from that in the right hand. We have just U1 symmetry times time translational symmetry. With this rotating background, this is broken down in this U1 sub, where you mix this U1 symmetry and time translational symmetry. Then again, we predict one non-Boltzmann model, which is often called the phonon. It's just a non-relativistic version of the action basically. So then you can just look, actually derive in part of a theory, you can derive the dispersion relation of the fluctuation around this rotating background. So depending on the just the parameter, right? So in this solid line, we have, so it corresponds to the case where rotation occurs at the body of the potential with a large angular momentum. So then you can find a phonon mode that has no mass gap, and the other gap, which just corresponds to excitation of radial direction rather than angular direction. We are interested in cosmological constant context. We are interested in the some microscopic length there, so which corresponds to small k. So then it's convenient to just look to linear dispersion relation. It is so then the frequency is just given by sound velocity times momentum. And sound velocity can be computed as a function of the potential to the radial direction with this formula. So you can see that when the field is not at the minimum, so where this second term is non-zero, this sound velocity deviates from 1. So on the other hand, if you add the minimum, we are at the potential when the potential derivative with respect to potential vanishes, the sound velocity actually goes to 1. So that corresponds to those dashed lines. What happens is that in the early universe where the charge density is large, we first have a phonon mode that whose dispersion rate significantly deviate from that of vacuum action. And those phonon modes are continuously converted into action. So then, how can you produce this phonon? So there, this is the cosmic perturbation plays important role. So in the standard cosmological theories, we create the perturbation of the infraton field, and that is converted into the perturbation of what we observe, like photon perturbation implicit in the CMB or baryon dark matter perturbation implicit in the large scale structure. So likewise, in this setup, this infraton perturbation can create a perturbation of the U1 charge density, which is nothing but the phonon or sound wave modes. So then those created phonon modes are converted into the actions via the cosmic expansion. This is what I call acoustic misalignment mechanism. So we can just use a standard cosmic perturbation theory to compute the abundance of the actions produced by acoustic misalignment mechanism. So some formulation to do so has been developed in a paper with Csaki and our collaborators. We should be slightly careful about computing the rotation, computing the perturbation, because final action balance is really sensitive to the equation state of this rotation and the sound velocity of the phonon. So for example, if you consider ordinary quantum potential, when the rotation occurs here, not surprisingly, the perturbation resembles that of the radiation, with the sound velocity square slightly 1/3. For example, in this phase, there's no growth of the fluctuation. So this early phase is not so important in determining the action abundance. But on the other hand, in certain supersymmetric theory, the radial direction is nearly quadratic when the radial field value is much larger than the decay constant. So then, again, not surprisingly, in the early phase, this perturbation behaves like that of matter with a very small sound velocity. If this rotation dominates the universe, we should take into account the growth of the fluctuation, like this matter perturbation grows in the after matter radiation equality. But anyway, you can take care of everything using the cosmological perturbation theory to find the evolution like this. Here I consider the nearly quadratic potentials. So x-axis is a scale factor, y-axis is how much perturbation grows. So and after the mode enter the horizon, we have a linear growth because it's almost matter line. But at some point, the sound velocity becomes non-negligible, and this mode began to oscillate. Then once the action rotation hits the minimum, the perturbation grows again. But this is just because zero modes, which only has the kinetic energy, decrease very rapidly. Then we can see all of this using a standard cosmological perturbation theory to find the viable parameter space. Here I assume some certain type of supersymmetric model. So then we found that in this orange shaded region, this mechanism, acoustic misalignment mechanism, can explain the observed dark matter density. We somewhat expand the parameter space in comparison with the kinetic misalignment mechanism. One thing that to notice here, I assume that infraton perturbation solves this action phonon perturbation, namely I assume adiabatic perturbation. If you introduce independent isocoverage perturbation action, we can expand parameter space even more if you want. Then let's further assume that the binary symmetry is created by action rotation and a Higgs Baryon process. So then we can slightly sharpen the prediction. Unlike the kinetic misalignment mechanism, since this amount of dark matter produced by acoustic misalignment mechanism is somewhat more model dependent, we don't have a prediction as a line, but just we have a prediction as a region, like this. And the prediction is even larger than just this green line. Here a summary. So rotation action can create matter antimatter asymmetry. This rotation also produces action dark matter through phonon mode excitation caused by cosmic perturbation or through parametric resonance. Action couplings are predicted larger than the prediction of misalignment mechanism. We don't have much time to have a more astrophysical topic, but I just say a few words about this. In those mechanisms, action dark matter is produced as a fluctuation, not a zero mode. So there in some parameter space, they can be warm to affect the structure formation. But there's also some interesting connection with gravitational wave physics. So this equation states the rotation modify the expansion rate of the in the Earth universe, and thus can modify the spectral gravitational wave produced by inflation or topological effects such as a cosmic stream. It gives an interesting signature. And this growth of the fluctuation and a subsequent rapid oscillation of fluctuation can also produce gravitational wave by itself. That's another interesting astrophysical topic. So anyway, that's all I want to talk today.
Thanks for the great talk. So in the kinetic misalignment case, you talked about this axion fragmentation where the zero mode generates finite K modes, and that seemed to be where you were getting most of the production from. But I could imagine getting production just from the zero mode, like basically once it loses enough kinetic energy, it just becomes normal misalignment. Is there ever a case where that dominates over the backstand rotation?
Yes. Indeed, that also contributes to action that matter. So if it's close to, really close to this line, it has found that mechanism don't work. But it has also found far away from this line. Actually, this parameter resonance is more effective than the simple zero mode oscillation. That's why I stress this parameter resonance aspect.
For the gravity waves, what's the frequency range, or what determines the frequency there for this?
So it's roughly determined by when the gravitational wave from the action perturbation is dominantly created when this rotation reaches the minimum. So it depends on when that occurs. Unfortunately, in the QCD axion, the frequency too high.
Yeah, that's
unfortunately.
Yeah, that's
but
what
for Axion-like field, it can be actually of lower frequency.
So this would push us into the high frequency gravity waves part of the spectrum.
Yeah, for QCD actually.
Yeah,
it seems to be difficult to detect
according
to
that
total case.
Yeah, right, that's right.
Okay, if there are no further questions, let's make that day again. All right, so our next talk is on Stasis Cube, Universe on Pause by Dienes.
All right, so it's a pleasure to be here. I'm going to do something really non-traditional. If you know anything about opera, you know that Richard Wagner created a new way of performing opera, which was never done before. He said the important thing is what's happening on the stage, not the people who make the sound. And so he submerged the orchestra into a pit so you don't see them. I'm going to submerge also. Okay, so I'm going to talk about stasis. I've taken an informal poll. Not many of you have seen it yet, so I'm going to start at the beginning. Unfortunately, this is work that has been going on now for 5 years. There's a lot of papers here, and when you are in a stage where you're working on the same thing for many years, developing it, you tend to have big talks that you can't cover everything because you have so many papers, but you need to start at the beginning. So that's what I'm going to do here. So I have 90-something slides. I'm not going to show them all. And I'll just skip, I'll go through the beginning carefully, so you'll all know the main idea. And then I will skip around to things that I think are interesting, including the most recent papers. This is work done with a former postdoc of mine, Lucien, who is also a former graduate student of Emilian, who's sitting over there. Fei Huang, who's a former student of mine, but a former postdoc of UC Irvine. So that's Yuri over there. Dujun Kim, who's now a new professor at the University of South Dakota. So in him is all our connections to what's happening at Dune. Tim Tate, who's also at UC Irvine, and Brooks, who's sitting back there. So all these people are around and can jump in if they don't like the answers. I give questions. Also involved in some papers is Dan Hoover and Anna Paulson, who are at Brown. Is anybody here from Brown? Anyway, they were former undergraduate students of Brooks's, and my current PhD student, Jonah Barber. So here we go. So I'm going to do something again that I don't normally do in a talk. I'm going to give away the punchline because I don't want you to miss anything. And I'm going to say it as strongly as I can. So we're used to the standard lambda CDM timeline, which had inflationary epoch, a reheating epoch, a radiation epoch, and then a matter-dominated epoch, and we're maybe entering a new vacuum energy-dominated epoch. And these are dominated by the energy densities. Imagine if I'm plotting abundances here. Most of them are 0, but then at some point, well, shoot to 1 like here, or here. This is matter-radiation equality. So the radiation abundance is 1, but then it falls rapidly at a certain point, and this is power law, of course, behavior. Radiation domination is 0, it shoots up to 1, and now we're here. So all these different colored solid lines are the different kinds of abundances, and they trade places. And at the times when they cross, you can have sort of order 1 equality, but that's unstable and it goes immediately to another dominated epoch. So that's the standard timeline. My message is if you believe that physics at higher scales is governed by some sort of BSM physics, pick your favorite theory. Extra space-time dimensions, strongly coupled sectors, string theory, almost everything, not always, and I'll talk about when it's not going to be this way, but generally, pick your favorite theory, then this picture is likely wrong. And I don't just mean that there's some extra little thing that has been missed, but not modified or generalized in some way, but rather a big piece is missing. And what's missing? I claim that there's a whole new type of epoch that has to open up in the early universe. And this is what we have dubbed an epoch of cosmological stasis. And this has been missed now completely in most discussions of lambda CDM, physics, and early universe cosmology, but in theories like this, it's there. And I'm not going to say we want it for certain reasons. I'm saying it's there. And if you have a theory of this sort and you haven't taken this into account, the burden is shifted on you to explain why not. So what is stasis? It's a cosmological epoch during which the abundances of different energy components of matter, radiation, vacuum energy, these all have different equations of states. You can separate them into different kinds of energy. These abundances remain constant despite cosmological expansion. So here I just happen to draw the abundances, this epoch of stasis happening between an epoch like here, but it could have happened earlier, could have happened later. That depends on the theory beyond the standard model that you're working with. But that's the idea. I also drew here a case of matter radiation equality extended, 50-50. That didn't have to be. It could be 70-30. It could be any numbers. But the idea is it doesn't change. So the universe continues to expand during such a stasis epoch, but the abundances stay fixed. So time passes as measured in E-folds, but not as measured in abundances. So already you should have a million ideas in your head that says this is garbage. The first thing is energy densities for each component scale differently with the scale factor, so how can they have ratios that are constant? I'm going to tell you, yeah, we can. It's a fundamental epoch which need not be dominated by any one component over many E-folds. If you could arrange this somehow, you might think, well, okay, if I had to fine-tune something to make it balance exactly. No, it's not fine-tuned at all. Even if it can be done with without fine-tuning, why should the universe happen to fall into such a balanced state, a stasis state? Well, I'm going to tell you it's an attractor. It's a dynamical attractor. Even if you're not there, you're going to head towards it. You really don't have, you really can't avoid it. Okay, you could say, well, even if it's an attractor for one model of BSM physics, what happens for different models of BSM physics? I'm going to tell you it's fairly general. The attractor behavior survives across a wide swath of BSM models like the ones I talked about. And it happens for a wide range of parameters within each model. So you don't have to pick, if it's KK tau, you don't have to pick the radius exactly. It happens. Show you pictures. All right, stasis sounds like an eternal thing, right? Once you're in stasis, you have stasis, which is the reason for the title like that. So how could it form the basis of a finite duration cosmological epoch? Well, it turns out that stasis comes with its own mechanisms for starting at one time and ending later on, with a potentially large number, tens, let's say, of E-folds in between. No problem either entering it or exiting from it. So here's the critical question. If my energy physics is indeed governed by a BSM theory such as things in that class, extra dimensions, strongly coupled sectors, or string theory, am I saying that the early universe will necessarily experience a stasis epoch? So what's going to come in the next bubble is carefully legalistic language that has been agreed to by everybody in our collaboration. Yeah, we are saying that. Now, there are, of course, important provisos and caveats. But the critical point is that such stasis epochs are a rather generic feature of such BSM cosmologies. And if you don't take them into account in your favorite BSM model, then really the burden of proof has shifted. And you should be prepared to explain why it fails to arise in your model if you're not thinking that it's there. So, yeah. Okay, so the basic idea. Now I'm just going to try to cover the basic point here. What's so special about BSM? Well, a wide variety of these sorts of models predict towers of massive unstable states. This is the key for most of stasis, but not all. But for what I'm going to start with. And for example, theories with extra space-time dimensions, these are the KK towers. Scenarios with confining dark or hidden sector gauge groups, Well, they have towers of bound state resonances. Or string theory, which has infinite towers of not only the KK winding states, now also winding if it's a closed string, but also string resonances. And this is true for all the bulk fields, such as string moduli and axions, we've been hearing so much about. In fact, there are even scenarios, which are very common in the PBH literature, primordial black holes, which lead to the production of PBHs with extended mass spectra. And these would be the different masses of the towers of PBHs. And in general, all these states and all these theories share certain very generic properties. These towers of states are potentially infinite. They can be bounded by a relevant cutoff very high, but there are many states. I mean, if it's a KK tower, this is TeV scale splittings all the way up to what might be the fundamental scale of the theory, Planck or string or something. So they stretch across many orders of magnitude in that. And such states are generally unstable. There's nothing going to protect them, and they'll decay. And you can even say that there are two generic features that govern how these things decay. The heavy states at the top of the tower are going to have the largest decay widths and decay first. Then the lighter ones and so forth. So the decays are going to proceed down the tower. This decays, and that decays, and that decays. And for any state, the dominant decay mode is to the lightest state available because it has the biggest cross-section. And so there's going to be the biggest branching fracture goes to the lightest thing around, which would be usually the guys at the bottom or something outside this sector here. And such decay products are therefore going to be produced with huge amounts of kinetic energy. They're going to be relativistic, and therefore they're radiating. So whereas you can think of these as matter states, they're going to decay to radiation. So what is the effect of having such infinite towers of states on early universe cosmology? I'm taking very seriously the idea that these states are there and they do things in the early universe. And basically the point is that the decays establish a sequential process working its way down the tower, which continually converts matter into radiation, as I just said. Now this seems maybe a little bit trivial, but there's actually a competing effect which pushes the other way, cosmological expansion. Because that, you know, remember radiation scales like 8 to the minus 4, where this is the FRW scale factor, but matter scales like 8 to the minus 3. So even if nothing else happens, cosmological expansion causes the relative fractional energy densities, the abundances, these are what abundances are, the relative fraction of the total energy density of the universe, the abundance of matter and radiation to change. In particular, due to cosmological expansion alone, the abundance of radiation drops because this is dropping more rapidly than matter, and the abundance of matter, therefore, is correspondingly rising because the sum of this is 1 if we're just dealing with a matter radiation universe. So indeed, that's the mechanism, well-known, standard cosmology, for how a radiation-dominated universe becomes matter-dominated simply as a result of cosmological expansion. So we have decays along the tower convert matter abundance into radiation abundance. And cosmic expansion does the opposite. It converts radiation abundance to matter abundance. So the natural question is, can these two effects cancel? And if so, then this would be a way of keeping matter and radiation fixed, but their abundance is fixed.
Now, Kit, are you assuming the entire tower was produced?
I'm assuming it was produced, and I'm going to tell you exactly what the assumptions are in about 2 slides. Yeah.
Right.
I'm just giving you the big picture right now.
Okay, but both in the extra dimension and homogeneous physics, right? When those states are produced through the phase transition, only the lightest few mode will be
there's an amount of abundance which is given to each one, and generally it falls as you go higher in the tower. But yes, I'll tell you exactly the assumptions. And I'm just trying to convey the main idea. Okay. These are the 2 things that are balancing in a matter radiation stasis. So what I'm going to tell you is, although it may seem like too much to ask for this to cancel, they can balance, they actually do balance, and even if they don't start out by balancing, the balanced solution is an attractor, and the system will come into balance all by itself. And this is especially remarkable if you think about it, because particle decay and cosmological expansion are very different things. The first of these is particle physics, the other is cosmology. And yet they want to come into balance as a dynamical properties of the equations of motion. As I said, I have a long talk here. There's a lot of, I have algebra here, which I can show you, but I just want to go quick. I don't want to linger on this. It's simple. And this is basic cosmology, just using the Friedmann equations. You find that in general, the rate of change of any abundance depends, of course, on cosmological expansions about how Hubble is changing, the universe is changing in its rate of growth, but also it depends on how the energy densities of each item change. And these themselves, this is where you're putting in what you're expecting for decays. So this is cosmological expansion. This is the decay, source and sinks, and you get an equation which tells you that the balancing of the decays is basically, this is what you need if you're going to have a stasis, is balanced by cosmological effects having to do with Hubble and the abundances you currently have. All right, now that just gets you it for one moment. This is just setting the first derivative of the abundances to zero. You need this to happen over an extended period. So you want this condition to survive at all times, and you get a constraint equation. Don't worry about it. It's this simple. That's all it is. The equation's here. I've not skipped any steps. Kappa is just Hubble modded out by the time, just because that's a more important variable. And in the end, what you get is some constraints that tell you about how the decay widths have to go and how the abundances have. All right, so we need to now say, well, what is our theory? What does BSM physics tell us about the actual abundances across the tower and the decay widths across the tower? And now I don't want to be tied to a particular theory of BSM physics. In order to talk about things in a general way, all the models I can imagine together, let me imagine a generic way of characterizing these masses. So here they are. I'm going to assume a tower of states whose mass spectrum is approximately or can be reduced to, in various well-founded limits, something that looks like this. So there's a ground state mass, and then there's a splitting, and then it can either be linear or power law, whatever you want. And so there are three parameters, m naught delta, m and delta. Don't worry about it. These have certain values if you're on a KK on a flat circle. If you're in a flat circle in the opposite regime, these values are different. If you're dealing with string theory, then we know that the mass squareds go like integers, so delta here would be a half. Let's just keep it arbitrary, and we'll let delta be a free parameter. Likewise, you want to assume something about the decay widths. This assumes on what kind of branching fraction, what kind of operator is finessing the decays. In general, for example, if the heavy states are decaying to photons, which is the lightest, easiest, the biggest cross section through a dimension d contact operator, just like this, then this gamma exponent will have a certain form and certain values. Likewise, at the time of production, so this is the question that was just asked. Yes, it's not true that they're all going to have the same abundance. Let's assume that there's some scaling relation, which is what happens in most reasonable production mechanisms, misalignment production, any kind of thermal production mechanism, whatever you like, they usually have this form with a different exponent alpha. Typically for misalignment production, alpha is negative, but either sign can occur for thermal freeze-out. We're being very agnostic. So alpha, gamma, and delta are the parameters. So what values can achieve stasis? And you can go through some algebra and you find that everything, all the complicated things you have to worry about, all reduced to a simple equation. Here it is. But this is not even a constraint equation, because the kappa bar, anything with a bar in it, is the stasis value of it. This will be satisfied, this, no matter what, any alpha, gamma, delta, this is actually a prediction for what the stasis value of kappa will be in the final universe that you have. And so this is not a constraint so much as a prediction for kappa. So as long as you're just in some very generous range, you will always have stasis. The corresponding stasis abundance, well, it'll depend on the values of these coefficients, but it will be a stasis. For example, if I choose numbers to make 2/7, which is very nice, because that will give me a half for this, I will have an extended stasis epoch with matter radiation equality. This is an actual numerical plot, solved not in any cheap approximations, but solving coupled Boltzmann code, no approximations, exponential decays, I mean the real thing. And here is what each different abundance is doing. The top of the tower, it decays first, and then it decays, and so it goes away. But the next guy starts to decay because he decays later, then goes away. The next one here, she decays later, so she starts to arrive, but then she decays, and so forth. And this is how each one is going down the tower. And the remarkable, and this is the final guy, but the remarkable thing is that the sum of this is a constant. That's it, right here. This is wow. To me, this is incredible. And this is just with 300 states, and look at how many E-folds of stasis already, 10 E-folds of stasis for 300 states. There it is. This is the picture.
But again, if you only have like order one number of the state,
then you'll have a much shorter period of stasis.
Okay.
But why would you have only order one when you have infinite towers?
like I said, if you
have a
produce
thermal
the
freeze out or anything else. So yes, I'm going to give you a formula for the number of states and how long the epochs last. So indeed, so you will obtain stasis regardless. So this was just one value to have it be 50%. But here's what happens if I choose different values. It will change the duration of the stasis as you see. Here's again the number of e-folds. This is incredible, 30, 40, 50 e-folds. And it'll change the value of the stasis abundance, but you'll always have it. Here you could vary even the Hubble parameter. When did you situate this in the cosmological timeline? It changes the rate of decays relative to cosmological expansion. So sometimes it overshoots or sometimes it undershoots, but it's always back into a stasis. This is a global attractor. You can actually calculate and verify, not just numerically, but analytically. Here are abundances, and you're always driven to some point, which was the stasis point. Here's again one with matter radiation equality. You're there. Okay, the question, once you're in stasis, how long does it last? It lasts until you've reached the bottom of the tower. Now you're out of fuel. There's nothing left. And then the universe naturally, gracefully exits from stasis. So ultimately, the number of e-folds depends on the mass ratio across the tower. And if there are n states that are participating, someone was asking about n, it will go like the logarithm of n. And that's why if you have lots and lots of states, you can get numbers that are of order tens of e-folds. It's the logarithm. Okay, so far, I'm moving topics quickly. I have lots of stuff we can talk. I'm going to be here. Also, I'm going to skip a lot of slides, but they're going to be posted somewhere so you can see them. So far, we've been talking about stasis between matter and radiation. W equals 0 and W equals a third. What about vacuum energy? W equals -1. You know where I'm heading. Well, again, cosmological expansion says that the vacuum energy density is a constant. So therefore, cosmological expansion, just like it tends to turn radiation into matter, it also turns matter into vacuum energy. So the pump, like in this case, the decays were like pumping. They were bringing you back from matter to radiation. That happened from decays. I'm going to call any process that gives it the opposite effect a pump. It's very natural. I just think of it as a pump from the point of counteracting the natural effects of cosmological expansion. What can convert vacuum energy back to matter? Well, we know from axions, you're damped, you're over damped, that's vacuum energy. You start to swing when you cross the threshold, the critical point with 3H equals 2M, and now you're swinging, you're basically matter again. This transition happens there, it converts vacuum energy to matter. Can that also lead to stasis like decay did? Well, you can work it out. There are some technical details. Again, skip. What happens though is that vacuum energy, each state of the tower, its vacuum energy goes along until such time when it's matter, when it's Hubble, 3H equals 2M condition is met, it converts, it starts swinging. I'm approximating here as a constant W, a flat W, and then it becomes matter. And so you could ask, does this give rise to a stasis between vacuum energy and matter? It turns out, again, you get a very similar equation. It's not a constraint, it's a prediction for the kappa you get. So as long as you're in this range, which is very natural and easy to satisfy, you will always have stasis. There's the final abundance. Here's a plot. Again, actual numerical plot. In this case, with the parameters we chose, which are down at the bottom, the numbers were 5/8 and 3/8, but it could have been anything we like. Okay, what about vacuum energy to radiation? Yes, again, same constraints, same very similar. Again, the numbers are a little more complicated, but there's always a stasis. All right, obviously you're thinking triple stasis. So far, I've shown you three kinds of pairwise stases: matter with radiation, vacuum energy with matter, vacuum energy with radiation. Each of these occurs in a universe that has only two types of energy components. But can we have a universe with all three in stasis with each other? Yes, but it's a bit more complicated because just because A comes into stasis with B in an AB universe, and just because A comes into stasis with C in an AC universe, this is really cool. And a B comes into stasis with C in a BC universe, right? Does not imply that A, B, and C will come into stasis in an ABC universe, because this is a more complicated universe. Each of these has a Hubble which cares about all three, even though only two of them might have been in stasis. But indeed, you can work out the algebraic equations, and it's very simple. And, you know, again, matter crosses the first line, it becomes, sorry, vacuum energy, and then it becomes matter, and then it becomes radiation. So every state starts as vacuum energy, then becomes underdamped, becomes like matter, then decays and becomes radiation. Or if you're looking at the tower, the bottom guys still haven't converted, and so they are still vacuum energy, but above a certain line, they have become matter. And then above that, they have decayed and become radiation. These lines are moving down the tower with time. So there are fewer and fewer of these and more of these. But cosmological expansion is pushing the other way and giving more and more of emphasis, more and more value to the abundances of vacuum energy relative to matter. And this is the balancing. And indeed, you can work out all the mathematics, and there are some subtle points. But here are some plots. Again, any numbers you like. Here's vacuum energy, matter, radiation. Notice the radiation, I could have it be the smallest, I could have it be the second, I could have it be the biggest. It can still be done. This is a general attractor. Okay, underneath what's happening in the tower is still very interesting, but the point is, this is an attractor. And so, you could ask, what's the attractor business? You can understand it intuitively by thinking of it as a W seesaw. We call this the W seesaw. There's a fulcrum. And here at W equals 0 is how much abundance you have of matter. Here at plus 1/3 is how much radiation. Here is how much vacuum energy at -1. And what's happening is cosmological expansion is trying to emphasize increase these values and decrease those values. So it's kind of wanting to push the seesaw that way. But the energy transfers due to the transitions, the underdamping transition and then the decays, are moving things the other way. And all I'm saying is the seesaw wants to balance. And if you chose the parameters alpha, gamma, delta, right, the fulcrum will be at the center. So you'll kind of wind up with things that are close to matter domination, but it doesn't have to be. If you chose other values of the scaling factors, the fulcrum is in a different place. But always it wants to balance. This is what's really happening here, which, you know, we were very happy to discover this. And again, all of these are stasis, all of these are attractors. And so here, again, is what happens to vacuum energy, abundances, matter, radiation. You can change the Hubble parameters when you start, doesn't matter. All right, you can work out a phase space for this, but very interesting. You can actually say, but we imagined that the fields were just fixed at vacuum energy, W equals -1, matter, W equals 0, radiation. But in reality, if we really want to treat these as dynamical scalars, and those that you work on Axion to inflation, you know that really what happens is your field, it will do something and then it starts to swing. And the W values, which are the orange here, are not changing, they're changing constantly. Could this come into stasis, the slow roll energy versus the oscillatory energy? Because we're not even having things be constant anymore. But incredibly, here it is. Once again, no matter how you choose the masses, you'll go into some kind of stasis, this slow roll abundance. And of course, the matter would be 1 minus that. And so this happens. This even has some incredible properties. I'm almost done. One of them is what we call tracking behavior. If you come into stasis, your system will have a W that comes into stasis, and then depending on some background value of some other field, it will come into stasis and match it. It tracks it. And it would stay there when you're in stasis, except that maybe you change the background value to something else. Some other physics happen, doesn't matter. It then shifts, the whole tower reconfigures itself, the seesaw swings again for a while, and it'll match it again. And if it increases again, it'll change again. Or if it decreases, it'll come back to normal. This is tracking behavior, which is incredible. Stasis tracks anything else that's happening in your system for that example. Which leads you to the realization that if stasis involves vacuum energy, then the stasis epoch could have any W between -1 and 1/3. And this therefore means that if it's less than -1/3, this could have an accelerated expansion, almost done. And so the stasis epoch can actually potentially be the inflationary epoch. This could be what inflation is. And that is an interesting idea because it doesn't require a complicated potential. Any W less than -1/3 is realizable. It's not just W equals -1. The number of E-folds of this inflationary epoch is related to the hierarchies in particle physics scales. In the KK tower, the start and end are related to the UV cutoff and the compactification radius, and then you would make a big claim that the universe is large simply because the Planck TeV hierarchy is big. A graceful exit naturally arises when you reach the bottom of the tower. And note, because you've been carrying along a matter abundance, reheating is very different because you didn't inflate it away. Each individual mode inflated away, but the constancy of the stasis epoch kept the total abundance to be fixed. Of course, in order to make a serious statement that this can work, you need to calculate the inflationary observables in order to test the ultimate viability. We haven't done that. We're doing it, but we think this idea is very exciting. All right, there are other contexts. There can be thermal stasis. In this case, you don't need a tower of states at all. I refer you to this paper. I assume polynomial scalings for abundances, but it can also be exponential, as in the Axiverse. I refer you to that paper. There can be stasis that emerges from theories where the particles have field-dependent decays. Again, stasis emerges. Trackers seems to be everywhere. My students and Brooks and I have worked on why this is the case. There's a deep underlying principle and some symmetries, and I'm not going to be able to talk to you about it, but it's there. Can you go beyond stasis? Yes, because there can be variants. For example, if you have radiative corrections to these abundance, to these scaling exponents, maybe they aren't exactly fixed at some fixed numbers. Doesn't matter. What was the scaling solution can now maybe puff out because of radiative corrections. So maybe it doesn't stay exactly constant, but vary within this band, and this can vary, and this can vary. Here we assume 10% variations, and still, notice, you don't go back to the usual fast crossing. You still have effectively a stasis. It's very robust. Or maybe what happens when the spacing between the states becomes large. Then you don't have time for them all to keep track with each other. So first you might decay, and then inflation take the expansion of the universe, and then it decays, and then another one, and step by step. And what you wind up with is an oscillatory stasis, where first the step happens, but then the compensating step, then the next one, and then the compensating step, and so forth. This resulting universe has a time average value, which is a stasis, but it can go through these breathing modes. And this is what the scale factor would do. This is the early universe. We have no data there, but think of all the possibilities that could be. You could avoid stasis. You're on the attractor line, but maybe you ran out at the bottom of the tower. Maybe there wasn't a big tower there. And so you're heading on the attractor line, but before you get to the end point, you don't reach stasis, and then you come out again. Okay, that is one of the few ways in which a pairwise stasis can ultimately be avoided, but it still changes the phenomenology because you experience that attractor for a while. There are observational signatures. I was writing this yesterday. I just want to tell you that you can modify the predictions for CMB observables. There's a paper on that. Stasis can modify the spectrum of stochastic gravitational wave backgrounds in certain ways, and even density perturbations grow in a very different way. And I just want to show you that, for example, if you're in a stasis, you get density perturbations that grow linearly throughout, parallel growth throughout the stasis epoch. Normally, in a perfect fluid, it always saturates and hit a plateau. But in stasis, it doesn't. So, yeah, I think it's exciting. This came out a while ago. We all thought it was exciting. So to conclude, this is another kind of cosmological epoch that hasn't been considered before. And it may be necessary to rethink the entirety of cosmological timeline if you're dealing with a BSM theory of the sort that should do this. We're only at the tip of the iceberg in spite of all those papers. There's a lot of things we still need to look at, and we're looking at them now, but it's exciting. I'm happy to answer questions now or later. I went over time, but thank you very much.
According to your calculations, where we are now?
Where we are now is where we always are now. The question is, when did this happen in the early universe? That depends on what model you have and what parameters you chose for it. So if you're talking about a KK theory, was it flat? Was it warped? If so, how much? This will determine the mass scales involved in those towers, and that will determine then when this would have occurred. but it will still lead to a stasis. It will still deform the evolution of the timeline.
So there's no way.
We see there are constraints. You don't want it to happen too much after BBM. We know too much about the universe then.
Yeah.
Although it's possible we're exiting a period of stasis now, but that's a different theory. And well,
what kind of experiment you have to do? What kind of experiment or measurement or observation you have to do in order to figure out which epoch we are now?
Well, right now, we know a lot about now. I think what you're really asking is, how can we find out what happened earlier? How can we?
Yeah, well, the previous step, which was,
right?
So
we know everything since BBN, more or less. And so we're talking about early universe. We're talking about very early. And so that's why I'm showing you pictures like this, where stasis is happening well before the present epoch.
Okay.
And what happened and when could affect things that we can see today. For example, I had a list. Structure formation, of course, is the biggest one. But these other kinds of things that we can see in the CMB spectrum, we can actually measure them. And the values, the predicted values, would change. And the stasis would disturb this in a certain way that is correlated with how it would disturb density perturbations and change structure formation. So just any one of these might suggest stasis, but maybe by looking at several of these together, you can actually triangulate and constrain which stasis model it was. So again, you learn about the early universe this way as you would in any other way. I'm just saying there's a new idea out there, and I think people need to pay attention to this if you're dealing with that kind of model, because it's an attractor. If we weren't an attractor, I'd say, okay, it's cubed, you can balance it mathematically, very nice, but it's an attractor. It's there.
Like John, anything?
QCD has a tower of states. How long was the QCD stasis?
Brooks, any idea?
So this is just sort of speaking off the cuff here. One of the things that you kind of need, right, that Keith had sort of shown is the parameter, the scaling relations for how the abundances scale and how the lifetime scale and things like that kind of give you, a sense of whether there's a certain range of parameters that you can get stasis or not. One of the things that Keith and I showed eons ago when we were working on this other concept called dynamical dark matter is that when you have towers of hadrons, you tend to get, when you're getting these produced, they tend to have sort of an exponential kind of Boltzmann suppression if you're just producing them in a phase transition or something. That ends up giving you a scaling relation that actually has a negative value of alpha, and that's a little harder to get stasis with, but it's probably possible in some realizations, we haven't thought about it too hard, that you could circumvent that in some way.
We did worry a little bit because the constraints are always on alpha plus 1 over delta. So you can tolerate some negativity in alpha if delta has the right signs and balance it. But we did not make that claim. So yeah, this is not dynamical dark matter, which I would love to connect this to, because that was something Brooks and I worked on 10 years ago, but we don't see it. So I didn't say the words.
I think Howie was first.
If your only power is the usual 0 to m Planck, 2m Planck, etc., does that put you back in the usual universe?
That's going to be hard because now you're dealing with super Planckian physics, and I don't know how to model it very well. So if you're talking about string resonances, then yeah, that's usually going to be the scale. And I don't want to say yes or no on that. But if you have large extra dimensions, even in a string context, you'll have string states, you'll have winding states, and all of those, depending on the radius, can be part of this. And definitely do that. There is a paper looking at the exponential behaviors that would come in an actual string theory. This is Halverson had a paper on this. So yeah, the scale is a phenomenological issue, not a theoretical issue as far as the structure of the equations and the fact that they give rise to any track.
Okay, maybe in the interest of time, we should leave the other questions for coffee.
Quick question. So
It should be in relation, right? For the
Thanks, yeah.
initial abundance. How we should be the first step. I'm wondering if you throw in order one factor.
Actually, had another question.
Order one.
How much is this factor?
Any order one.
If I still have some maintenance as well, if this momentum,
Order one unrelated.
Yeah,
with an initial abundance.
So look at this. So you know, after stasis
second, and so I went to the agreement. But we do market on this last
Just really like that. So I'm sort of skeptical with it. The other hand, so therefore I was find that these general
depths of states and
then we have to observe.
Yeah,
has been in some studies. That will tell us that it's somehow
But yeah, your equation, if I threw in one factor, I don't know if
you say that there's a large
state relations are growing better than right? So this is
better than acceleration.
One fact things are also flat stasis. You'll get yeah, absolutely. Good to see you, bud.
Good to see you. So yeah, especially the evolutionary aspect of this is really interesting.
Yeah, let me make one precise. Precise statement. Well, just start. Yeah, so that's why you start, right? Fundamentally,
you're using this is going back to
this is really so that happens enough from we only talk about yeah. So then
that's probably the species is tenable and the radiation state is tenable.
Precise radiation mediated by this built correct built in its original primary vertex, unless it is addressed up with other stuff.
Like the standard
that was the question. So now, yeah, since you have a completely different dynamical calculation you have done. It's
then we never really Instantons goes and down star and straight
okay, yeah, no worries. Let me, I was about to say, let me stop that for a minute and I will get back to you. These are great questions and I definitely want to.
However,
so we sort of assigned everything.
Yeah. Oh, the exactly here that to see
no,
absolutely. I mean, this is one of those things where there's so many things that we look at, and like I remember looking at mechanical stuff in this program at some point. There was some like
divided by
is also like animation in some ways, but not exactly. And it's kind of manipulation in some ways, but not exactly. And let me get back to you on that.
Okay.
Chat
I guess there's some assumption here that like they come out
And then they said, so the words are going to be the slides of the very interesting to see.
By typical act like sign, you need just adding. There's some limited sign, and that's why you like I have higher
That is really so.
Okay, I guess it's more suppressed. Like this is the PQ rating here, so like the more suppressed that is, the less
it can be compensated by taking larger initial I guess it's just related with the relation between potential gradients, the radial gradients. Gives maybe as of end you can write keep design maybe success by
Any email exchange with him yesterday about something else.
Okay. All right. Yeah. That reasoning. Summary of the argument is harder to get rid of.
Very nice guy. He was interested. He was interested in stasis.
Yeah.
Yeah, because he saw that about us. We saw that on store, and he said, "Oh, do you fund this?" Directly, I do have money for my program. Does fund Brooks and all these other people, but I'm conflicted. And he said, "Oh, so you can work with them on this too." And he's like, "Oh, you got time to work."
So that we can go.
No, so most of the program was
no, don't say that.
Yeah, I mean, it seems like maybe I just use more complicated ones than this. For the most part. Okay, but
Risk is what we say. The federal government word for forcing you into unemployment. It's called reduction in force.
You told us.
Oh no, yeah. I mean, I like sort of more on the
but you know, his language should not be that like indefinite.
I see you, but yeah,
I think the center would expect is stable enough
to my glasses.
Survive. But they need to never know.
Right. So before the start, I want to make a short announcement about the dinner. So we're going to have a dinner at Terning, and Terning is brewing. So even if you're not planning to bring alcohol to get into the building, they will ask you for an ID. And I advise everyone to bring their physical copy of an ID. So a photocopier in your phone might not work. We had that problem with other products in the past. So I advise you to all bring your physical ID, photo ID. And second, it's a bit far away. So there are like various ways to get there. So I suggest that like 15 to 20 minutes after the last talk ends, me and other products will meet you at the lobby of the graduate hotel. And then like if some people want to walk, like some of us can get these people and walk with them, and other people can take the train. For example, I can assist those people in like buying tickets and showing the train and walking them there from the final train station to the Sterling. So as 15 to 20 minutes after the last talk ends, we will meet you at the lobby of the graduate, and
You're not forced to come with us. You might like prefer to take an Uber or like walk for yourself. But if you opt to do it, so we will be waiting for you. Yeah.
How long is the walk about?
Yeah. So it's like I'd say it's 35 to 40 minutes roughly. If you first if you walk fast, but you should be aware that like, there is a tension. It might rain tonight, so it's unclear, but like it might. So you should keep that in mind. Yeah. Otherwise, we can take a light rail, and it's 2 stations, and then it's other 10-minute walk. Yeah. Okay. So with that, we are pleased to have Karim to tell us about the instantons. So this.
It's a pleasure to be here, and this is work done with Csaba Csaki and a bunch of his friends and my friends too. And I'd like to thank the DOE for their generous support. So, continuing with Raman's theme, we'll take a nostalgic trip back to the exciting physics of 1984. In spring of 1984, the most exciting thing happening was monopoles. So I'll give a lightning review of monopoles, and then we'll talk about the big thing, Rubikov-Kalin, and then we'll see what instantons had to do with that story. Okay, so the most important thing in the talk that you should remember is even more nostalgic, 1904. I remember it well. J.J. Thomson discovered that an electron and a monopole, just sitting static, have an angular momentum proportional to the electric charge times the magnetic charge points from the electric charge towards the magnetic charge. That's the one thing you should remember from this talk. Okay, so 1984, there were all these problems with monopoles. Weinberg had shown from first principles that electrons scattering off monopoles, their scattering amplitudes violated Lorentz invariance. And then 't Hooft and Polyakov showed that there actually are monopoles in gut theories, so what are you talking about? Another problem is that if you try to construct scattering amplitudes, you'll find that it doesn't make sense if you follow the usual Wigner prescription that you just take tensor products of one particle states to make your asymptotic states. So then they didn't know what the answer was. Nowadays, we're much smarter. Or we live in a later epoch, so we know the answer. The first half hour of the talk will be explaining this, and then the second half hour, I'll go through this. I don't have an hour and a half. Okay, I'll just tell you that the answer to this is that you have to take into account that angular momentum that J.J. Thomson told us about. If you do helicity amplitudes, you need to construct states that include the pairwise helicity that depends on the two particles, not on one particle states. And so if you specify two particle states, you specify helicity in your helicity, pairwise helicity in your helicity amplitude. And then everything works the way Wigner told you it should work. The last problem, Rubikov and Kalin had shown that there was monopole catalyzed proton decay where 2 U's come in and ED goes out, and it's not suppressed by gut scale. Incredible. And then Kalin went on to show that if you send a positron into the monopole, then you get out this mess, and it has a half here. And no one understood what the half meant because what's half a particle? And first attempt was maybe half the time you get the positron and half the time you get the proton, and that gauge charges are only conserved statistically. That theory lasted about 5 minutes. So then they just declared that this was a semiton, and then string theory was discovered. The first string revolution happened that summer, and everyone forgot about this. This one, we still don't have an answer, but in the last few years, several groups have proposed answers, and they all seem to, most of them conflict with each other, and no one agrees on what the real answer is. So that's the motivation for trying to understand Rubikov-Kalin, because no one understood that either, except Rubikov and Kalin. Well, maybe a few people. Nobody I knew understood it, let's say. So warm-up example, a simpler theory where we only have electrons and positrons, and we'll scatter an electron up a monopole. There's a selection rule if you take into account the pairwise helicity, there's the total angular momentum has to be bigger than the absolute value of the pairwise helicity minus a half. And so you can, if this is a minimal monopole, the pairwise helicity can be 1/2, and you can get a J = 0 state. Basically, the angular momentum in the field could be half down, and then your electron could be a half up.
What is F in your previous slide?
I can't show any slides right now. The computer just died. I don't know what it did.
The connection. Try to use the other USB-C.
Last slide was what was the question?
Next slide. What is F?
F is a fermion with a charge E, but let's call it an electron among friends.
Yeah, and F prime is another.
Well, it's going to have the opposite helicity. Okay. Because we're going to take massless fermions to make life easy. So what happens depends on whether the pairwise helicity, the angular momentum in the field, is positive or negative. If it's negative, you can only have a right-handed fermion go to the left-handed fermion. If it's positive, then the other way around. So you have to flip helicity in this lowest partial wave. In other words, the physics of the lowest partial wave is like a chiral gauge theory in a very peculiar sense. But it follows from angular momentum conservation. So you can just calculate this using the pairwise helicity formalism, and in 3 lines, you can get the answer. It exactly reproduces this paper from the 70s, where it's a 20-page paper of solving the Dirac equation in a monopole background and extracting scattering states. It's very painful. But you get the same answer as the 3-line calculation, so we're happy. Okay, so now we can move towards Rubikov-Kalin, the last half hour of the talk. So our friends, Georgia and Glashow, came up with this beautiful gut, has 1 generation in it, and there's a little SU2 block that this is the ordinary color and SU2 left. This SU2 block is obviously broken by the gut physics, and that sector has a tough Polyakov monopole in it. And so what's relevant for the monopole physics is just to take this SU2 subblock and then decompose that in terms of this gauge group. Then you have 4 doublets of that SU2. These will be plus and minus charges interacting with that monopole. And because if we look at the lowest partial wave, this is a minimal monopole, the lowest partial wave is J = 0. These top guys can only be outgoing, and the bottom guys can only be incoming. That's the chiral nature. And Rubikov-Kalin took this and said, what if we take 2 U quarks, scatter them off a monopole? We have some initial state, which we can make J = 0, and translate that into pairwise helicity states. And forward scattering is not allowed because if we go through the monopole, then the angular momentum in the field will flip because it has to point back to the monopole. But our spin can't flip because we're massless fermions. So we can't have any forward scattering. Usually there's too much forward scattering. So if we can't have forward scattering, there's actually just a unique answer, just like in the simple case, the warm-up case we did. The only possibility is that you go to E and D. If you look back at our list of possible final states, the ones that conserve all the gauge quantum numbers will be just the E and D, like they said. So there's our monopole catalyzed baryon decay. The only remaining question is, why does it work? Because it just seems like magic. You put in this magic gut physics, and you get out an answer, and it's not suppressed by the gut scale. What's going on? So there are a few clues left behind for us. One is that Rubikov and friends showed that E dot B is quantized in this process. E dot B is FF tilde. So this sounds like an instanton thing. We know that there are abelian instantons in two-dimensional theories in the Schwinger model. When you calculate ordinary vacuum polarization, this is actually related to an anomaly in 2D, and you get a mass term for the photon from this anomaly. If you look at the configurations of the gauge fields in this Schwinger model, you can have gauge fields that go around in a circle like this. Asymptotically, they approach the 2 index epsilon alpha beta x beta over x squared. And when you calculate the first Chern number, which is just calculating around this loop at infinity, you get a quantized number. And that's why there's instantons in these 2D theories. So we want to see if there's a connection between our 4D theory and this 2D physics. So in the monopole background, you can calculate the full Chern number, f tilde, which is E dot B. We'll split the integral up like this. So the monopole has radial magnetic field, so we can calculate the radial magnetic field over a sphere. That's nice because that will just give us the magnetic charge enclosed. And then what's left is to calculate the RDT of electric field. And I'll put in this vortex solution. I'm not going to tell you why I put that in until later. We're going to see it comes out of the calculation, but just to understand why it's relevant. If I put in that vortex field, we'll have a vortex that has three-dimensional spherical symmetry because it's around a point in, it's at some fixed R and fixed T. That means it's a spherical shell. So putting in that vortex field gives another integer, and we get pairwise helicity times an integer with factors of 2. So we get something that has it's a 4D abelian instanton solution, quantized, but it's got 3D spherical symmetry. Usually you're used to thinking about spherical symmetry in 4-dimensional Euclidean space. So this is a special type of instanton. Okay, so we want to see how we can relate these instantons to Rubikov-Kalin. So if we start with NF doublets of SU2, then the UV theory has an SU-NF flavor symmetry. We break that SU2 down to U1. In our U1 effective theory, the doublets will split into plus and minus charges from the top and the bottom. And the flavor symmetry will be SU-NF cross SU-NF. And so that doesn't match. So there must be more to the story than that. It actually is broken down to the SUN subgroup because there's a boundary condition at the place where the monopole is sitting, which we'll choose to be the origin. So at R equals 0, there's a boundary term. Lam and Yan worked this out in painful detail because Rubikov told them this would be an interesting project for you guys. I don't want to waste my time doing it. And so they found that on the boundary, from the SU2 theory, there's this remnant gauge piece split into our low energy effective field for plus and minus charges. There's terms that look like they violate charge, except this EDVI phi shifts under a gauge transformation. So this thing is called the rotor. So what this allows you to do is send in an electron and deposit negative charge on the monopole and come out as a positron. But that gives totally the wrong answer because exciting this rotor degree of freedom means you've excited the Dyon, and the Dyon is much heavier than the monopole in the gut theory. It's got a splitting of order, the gut scale times some gauge couplings, E squared M gut. So I'm just a poor guy. I can't even afford an LHC. I'm not going to have any gut energies in my incoming states. So we can just integrate out this rotor and never talk about it again. Okay. So in fact, let's take the gut scale to infinity, because the answer doesn't depend on the gut scale. We should be able to just see this in a U1 theory with this extra boundary condition. Okay, so we said we had this instanton solution, then we can solve the Dirac equation and find how many zero modes there are. And we can count them using the axial anomaly, because lots of time. Integrating this gives us, the difference in number of zero modes. So it's an integer, so this has to be an integer. And because of this boundary condition, it's relating two separate charges. So that halves the number of zero modes because they're no longer independent. Without the boundary condition, they would be independent. With the boundary condition, they're related. So that cuts them in two, which is great because Witten found that there were instantons with 3D spherical symmetry in unbroken SU2. And that leads us to a fun conjecture that 4D abelian instantons are EFT remnants of Witten's spherical instantons. And the evidence is that they have the same number of fermion legs. So he would have one leg, one zero mode for each doublet. We have one zero mode for each doublet.
A conjecture? You made a conjecture?
We made this conjecture. Because that's a cool thing to do, right? Just conjecture things and let other people prove them. It's a lot less work, at least. Okay. So let's just calculate the path integral and see what the answer is. And we'll do the warm-up example that we did at the beginning, where we just have a negative charge coming in and a positive charge coming out. That's the case when there's two doublets. And then once we understand that one, we can do the four doublet case, which is the full Rubikov-Cowan story. Okay, so we're interested in the lowest partial wave because that's where the magic happens. And there's no perturbative contribution because they're massless. There's no mass term I can put in their propagator to flip their helicity. So the only way this can happen is through some non-perturbative effect like an instanton. So we'll just concentrate on the instanton sector. And we'll write out the path integral and start, have to calculate the determinant of the Dirac operator, calculate loops, pain. But some of our collaborators are young enough to do this still. And they got this, plus other terms. This is the term that comes from the special chiral part of the lowest partial waves. The rest is just the normal stuff that you would always get. So let's focus on the interesting thing that's different. So you get, this is exactly the Schwinger mass term written in terms of gauge potentials. And it even looks 2D because these lowest partial waves that are chiral are, they have spherical symmetry. So they are effectively 2D. So because we're getting the Schwinger mass term, we have hope that we're on the track of the instanton. But we can do better than this lame perturbative calculation. We know that we could just take our fermions in the 4D theory and do a chiral rotation, and then we'll pick up an anomaly term. But because we have this chiral theory, if we choose this function that we rotate by in a very special way, we can decouple it from the vortex part of the gauge field. So here, ER is the radial electric field, which is for the spherically symmetric part of the gauge field. And SH is the sign of the pairwise helicity. If we make this crazy choice and use this relation for these vortex solutions that we saw, they satisfy this crazy relation. So if we plug this in to our Lagrangian term, we have our chiral rotations. They depend on this crazy function. And when the dust settles, it cancels out the vortex part of the gauge potential and leaves the background monopole field. So after this rotation, they see the magnetic field of the monopole, but they don't see the vortex. And we pick up an anomaly term. The anomaly term depends on the thing we rotated by. times FF dual, which you can write, if you plug in what FF dual is here, it's got a background magnetic field. So in the presence of the background magnetic field, you pick up this term, and this is that Schwinger mass term, again, written in terms of the electric field. So that Schwinger mass term was not an artifact of perturbation theory. That comes from an exact result in the 4D theory. And you can see it from a 4D calculation. You don't have to fiddle around with 2D approximations.
Is that a local change of variable or field redefinition, or?
No, it's got a 1 over d squared.
Yeah. So I have to worry about the subtle related.
I'm not worried. Are you worried? Why are you worried?
Although I cannot say exactly how I have to work.
Tim Cohen has a paper a few weeks ago about non-local field redefinitions. Summary is, don't worry. Okay, so we want to calculate our correlator of a lowest partial incoming wave and a lowest partial outgoing wave, fermion. So we'll put that in our path integral. We'll sum over all the instantons, and we'll integrate over gauge fields. We'll integrate over fermions. Here's the 2-point correlator we're trying to calculate, and e to minus action. So everyone recognizes this. I see nodding heads. So now we'll just do our rotate. Well, first of all, we know this can only happen in the instanton sector. And the higher instantons have more legs. So we need to pick the instanton that has 2 legs. That's the n=1 instanton. So we already know we can just look at the n=1 sector. Okay, now we'll do our rotation. So we have our primed fields that there should be some primes there. And we've got this extra piece in the action from the anomaly. Now, our fermion integration is easy to do because it's decoupled from the instanton. It only sees the background magnetic field. And the fermion integration just picks up the 0 modes of the instanton. And then I pulled a fast one on you because I said there's an instanton there, but I didn't actually show you why there's an instanton there. Why is there an instanton there? If we look at our action, it's got these phases are there from the fields that are inserted in the path integral, and it's got the anomaly. It's got both of those. So the rotation part acts as a source. The anomaly part is quadratic in the background magnetic field. So this, we can find the saddle point for this and do this path integral, but it's not an approximation. It's exact because this is a Gaussian integral. And the saddle point is our vortex instanton solution. So that's why there's 0 modes that are picked up by the fermion integration. And this exactly gives the pairwise spinor helicity result, which is exactly the Rubikov-Kalin story. Well, they didn't do this case, so it is the pairwise spinor helicity result or the Yang result. If we look at what the saddle point looks like, if I put my 2 field operators here in the RT plane, you see there's winding around these, and these are like fractional instantons at each fermion insertion, but overall globally, there's 1 instanton. And now we can do Rubikov-Kalin, but it's exactly the same story, so I'll just show you the picture. Now there's 4 fields in our correlator. There's 4 fractional instantons. They add up to an overall vortex. That's too much time. So this agrees with Rubikov-Kalin and pairwise helicity amplitudes. So I think now we know, I understand for the first time when we finish this paper, what Rubikov and Kalin were trying to tell me. They were trying to tell me that there's an instanton effect in a U1 effective gauge theory. It's related to instantons in the SU2 theory, but you don't need to know anything about that SU2 theory because all the physics is contained in the low energy effective U1 where the gut scale is taken to infinity. That's why the monopole catalyzed baryon decay doesn't depend on the gut scale, because it's just an EFT calculation. So I'm happy about Rubikov-Kalin now. What we're not happy about is the Kalin process, where instead of sending in 2 U quarks, you send in a positron. So I'd be willing to bet that it must have something to do with instantons. And several of the proposed solutions don't even mention instantons, so I'm just going to ignore those. The hard part is, in this case, it was sort of trivial going from Euclidean to Minkowski because we had these incoming and outgoing states. The single particle states looked like we can identify which ones could be incoming and which ones can be outgoing, so there's no ambiguities. But in the Kalin process, it's like we've crossed one of the legs, but there's no crossing symmetry. So it's not going to be the same, A. And B, it's not allowed to be there by itself, but it's got 2 other quark friends to be with. So that combination overall has to have J equals 0. And there is one unique quark state that has total J equals 0. Yuri can tell you about it if he wakes up. So that has got to be the answer if instantons are what explains Kalin's effect. The hard part is understanding going from Euclidean instantons to Minkowski instantons in a theory that doesn't have crossing symmetry. So that's what we're supposed to be working on. But the DOE tells me I can only work on Axion, so it'll be a while. So, conclusions. Pairwise little group determines monopole partial wave scattering amplitudes. I do that in the first half hour. Abelian instantons are the underlying mechanism for surprising results in lowest partial waves. Thanks.
Questions? Is this your addition of Kalin Rubakov Kalin rather?
Yes, Rubakov-Kalin is correct.
Rubakov-Kalin, I know.
Rubakov was first.
Yeah. So is it published? Did you publish it?
This instanton calculation is published, yes.
Recently? Or
last summer.
Last summer. Okay, thank you.
Help me. Yeah. Could you comment on? We recently heard a talk at Rutgers on this from Take Okui. I guess they published a PRL about they have the solution to this Kalin-Rubakov scattering where I'm already fuzzy on the details, but they have some effective Lagrangian for the fermions and the rotors, and they show that the particles actually just pass through each other. If you do that.
Yeah, well, I can say a few things about that. So we're talking about a left-handed fermion that turns into a right-handed fermion. So he says that multiplying it by a phase accomplishes that. I mean, maybe in 2D that makes sense, but in 4D, they transform under different groups. So multiplying by a phase is not going to change a left-handed fermion into a right-handed fermion. Secondly, the whole story depends on what the rotor is doing. But you didn't say anything when I said the rotor excitation is at the gut scale, so I'm going to integrate it out. So if the rotor played a role by the laws of effective field theory, it should have a 1/m gut correction if it's contributing anything. So that's 2 things I don't understand about. And thirdly, it didn't mention instantons, so how could it be correct?
So regarding the motor, there has been a proposal that instead of you need to excite the gut scale, Dyon excitations, what you can have is that incoming fermions as a kink, right, in the bosonized picture, can actually go through the spectral fluid.
Well, let me stop you there.
Okay.
I don't know of a bosonized picture in 4D. So what is the bosonized
This is
picture
2D
in
bosonized picture. So if we go to the S-wave channel.
Again, if we go to 2D theories, then lots of things can happen in 2D that cannot happen in 4D. So I need a 4D explanation, I think, but continue.
Right. So instead of needing to actually excite the Dyon degree of freedom, which causes, as you said, God scale energy, instead what can happen is that because of the interaction of incoming fermion with this Dyon sitting at the core of the monopole, you can go through the spectral fluid that you can go from the monopole ground state to the Dyonic ground state, which only costs energy of the order of the charge of the fermion that goes into. So this, I think, is the one logical way out of the
charge of the fermion is dimensionless. So the energy.
Charge mass. Yes, sorry.
It's the mass of the fermion. And Brennan has a paper in 4D which claims that there's a tower of states that are separated by the electron mass.
Yes. So that exactly.
I completely understand it. But
yeah, when I the paper, there's lots of things about W bosons being important. And the W bosons have M gut masses. So again, I didn't understand how the decoupling works.
So the claim was that there is no M gut gap in those additional states, but I don't understand how it works. Yeah.
More questions? Okay, so let's take it again. Okay, so
John,
would you like the mic?
I don't know. No.
Yeah, so easy.
Yeah.
Very good. I was actually about the story. It was in 4D.
That's good now. Yes.
Okay, so have a little bit later share those fascinating and looks and things.
Right. Yeah, so thank you so much for the invitation and for organizing the workshop. So I'm going to talk some more about using instantons. There are going to be monopoles as well, obviously, although in detail, what I'm going to describe is going to be a little bit different. And so what I'm going to talk about is in a paper that will appear very soon. Otherwise, some of these people might get murdered. Yeah, I'm with me. So this should appear very soon, maybe next week, hopefully. With my great collaborators at NYU, Ken Van Tilburg, and his student, Marius Concert. Cool. So, yeah, so I don't have to motivate this to this audience. We all agree that non-perturbative dynamics are really important to understand the structure and phenomenology of the standard model, and also many of its UV completions. So, in the standard model doesn't contain topological defects or even unstable defects aside from QCD, but in extensions of the standard model, whenever we have a spontaneous symmetry breaking, this is often accompanied by the formation of defects. So this can be of various types: magnetic monopoles, cosmic strings, domain walls, unstable defects like vacuum bubbles in a phase transition. And these appear in all sorts of extensions of the standard model, including very minimal extensions like, say, the QCD axiom, grand unified theories, as we've already heard, theories where we're trying to engineer baryogenesis, and so on and so forth. So this talk is going to be mostly focused on magnetic monopoles. So as I said, in the standard model by itself, there are no magnetic monopole solutions, but they are generic in many extensions of the standard model. So the original idea, the original sort of introduction of this possibility was due to Dirac in 1931. So he introduced the possibility of what would be sort of like a point-like Dirac monopole. The simplest toy model in which we can sort of complete this point-like monopole in a sort of non-Abelian gate theory is in the context of the Georgia-Glashow model. So that is SU2 is spontaneously broken to U1, and this is going to come up a little bit more later. Also, of course, in the context of more complicated grand unified theories, there are also generically monopole solutions. In theories with extra dimensions, in a string theory, we also expect to have monopoles around. In fact, monopoles are just so generic that one of the many reasons inflation was introduced a long time ago was partially also to get rid of all of these monopoles that were going to be produced as a result of a spontaneous symmetry breaking in the early universe. And it also motivated George Boczynski to postulate his completeness hypothesis, which just basically was just like a way of formulating the sort of expectation that in any sort of consistent UV completion, you should expect all dynamical objects that carry all possible charges consistent with the Dirac quantization condition. And so that should also let us to expect that any UV completion of the standard model, there will be some magnetic monopoles around. Of course, it's kind of a lie to say that there are no monopoles in the standard model. The moment we couple electromagnetism to gravity, just minimally, this theory does have magnetic monopoles. And those are just the magnetically charged Reichner-Nordstrom black holes. So the bottom line of this, and I'll come back to this later, but the bottom line is that these solutions are generic, either in sort of extensions of the standard model in field theory, or even when we just couple the standard model to gravity. And so it is important to explore the effects of these types of defects, especially magnetic monopoles in the low energy effective field theory. Okay. And again, they don't need to sort of exist out there in the universe as sort of like asymptotic states in order to potentially affect the low energy theory. Okay, so I'll do a brief recap of magnetic monopoles, and I'll tell you about our Abelian instantons, and then discuss some of the non-Abelian UV completions. So just again, a brief recap of the sort of standard field theoretic monopole, which is a Polyakov monopole that we find that is a solution of SU2 that is spontaneously broken to U1. And throughout this talk, I'm writing everything in sort of Euclidean signature, but mostly everything is kind of the familiar story that most of you already know. So this is just SU2 gate theory that is spontaneously broken to U1 through the web of a Higgs that transforms in the adjoint representation of SU2. This theory contains monopole solutions where the Higgs and gauge fields take some non-trivial profile of this form. So the Higgs here I've written in Hedgehog gauge, so the Higgs here has like in isospin direction, it points radially as a hedgehog. The AI component also has some non-trivial profile. These functions in general will be some complicated functions that you can only find analytically in certain limits, like in the BPS limits. But you can convince yourself that as long as they satisfy certain asymptotic and boundary conditions, this sort of field configurations do have finite action. Okay, so this has finite action field configurations. And if you look at them far away, they do look like they just source a magnetic field. So they look exactly like a magnetic monopole with a magnetic charge that is given by 4 pi divided by the gauge coupling. And then the mass of this configuration is of order 4 pi times the BEV divided by Dyon. Small, these guys are obviously very heavy. And then typically the size of the monopole will be set by, in this case, the mass of the W. there exist extensions of these monopoles that carry both magnetic and electric charge. So these are the so-called Juliet Z Dyons, which again are just an extension of the monopole that carries magnetic charge. And so this field configuration can be written in a way that is just like the Atuf-Polyakov monopole, except you are also allowing for the A4 or A0 component to now have a non-trivial profile. Okay, and so this non-trivial profile is what allows the field configuration to also source electric charge. So again, if you look far away, this guy, as I promised, looks like a Dyon carrying both electric and magnetic charge. All of these various parameters, so the profile of this A0 component is related to the electric charge, to the equations of motion, blah, blah, blah. There's also an extra mass that the Dyon picks up as a result of having these electric fields around. And so this is what I'm writing here as delta M. And again, in order of magnitude, it's also something that is proportional to the electric charge square times the mass of the W. Okay. So it will be heavier than the standard monopole by this much. So interestingly, if on top of SU2 plus a Higgs, we also consider the presence of a vacuum angle for SU2, so a theta term for SU2, then the spectrum of the various Dyons in the theory mix with each other. Okay, so the electric charge now becomes theta dependent. So for example, the sort of Atuf-Polyakov monopole that had 0 electric charge now becomes a Dyon, when theta is not 0. The first Dyon with k equals 1 will become entirely a magnetic monopole, when theta in particular is 2 pi, and so on and so forth. Also, the mass of the Dyons. So the mass of the Dyons, as I said earlier, depends on their electric charge. If their electric charge now depends on theta, turns out the mass of the Dyons now is also a theta dependent quantity. So at low energies, well below the scale of the spontaneous symmetry breaking, this looks like a theory of electromagnetism that carries both electric and magnetic charges, and also that has a theta term that is physical in that it is affecting the spectrum of these Dyons. So this effect is known as the Witten effect, and sometimes we summarize it by saying that this electromagnetic theta term, or the electromagnetic vacuum angle, becomes physical in the presence of monopoles. And this is sort of the simplest example where we can see that explicitly. So an interesting potential consequence of this that was pointed out a couple of years ago by these folks, Gigi Fan, Matrice, and friends at Harvard, is the following. So, and they were motivated by thinking about axions in general, the QCD axion in particular. So we know that the QCD axion in general couples to electromagnetism at low energy, and it couples to electromagnetism in particular through this coupling to the E dot B term. Okay, so this F here really is the F of electromagnetism. And also for axion-like particles, this is one of the most used couplings to look for this type of new particles. So the observation was that through the Witten effect, if our theory also has at some level magnetic monopoles, through the Witten effect, those Dyons or those monopoles are going to become Dyons, and their masses are now going to be theta dependent. Okay. If I now compute the contribution to the vacuum energy density from this spectrum of Dyons with theta dependent masses, the vacuum energy density is going to depend on the Dyon mass, and if the Dyon mass depends on theta, this is giving me a contribution to the vacuum energy density that is theta dependent. And theta, again, is the theta term of, in this case, electromagnetism, or if you prefer, the expectation value of these axions. So sort of the intuition of these guys is that these Dyons will generate sort of a theta dependent contribution to the vacuum energy density. If this thing really is a dynamical axion, that might suggest that in theories with monopoles, there is yet another contribution to the axion potential, okay, beyond QCD, that is generated by magnetic monopoles, and that depends on this, again, on the axion or theta. All right. Very reasonable. At least sort of qualitatively, what these results suggest is that if I wanted to describe this sort of contribution sort of theoretically, is that there should exist, in the presence of magnetic monopoles, field configurations, configurations of Abelian gauge fields such that this quantity, the integral of f with f, is not zero. And so we've seen some examples of Abelian field configurations in the talk right before, where things like this can happen. What I'm going to discuss here is the sort of field configuration that we believe explicitly captures this sort of physical effect that Madrid and company sort of, I think, identify correctly, if not maybe in like full detail. So let me just remind you a little bit about, before we move on to discuss Abelian instantons, let me just remind you a little bit about the various data terms that we read out in the standard model. So if you're just new to the standard model and you ask, okay, what other dimension for operators I can write? You might start by writing a theta term for each of the various gauge groups, right? One for hypercharge, SU2, and QCD. We typically sort of ignore the hypercharge, the U1 theta term, because there are no U1 instantons. Okay, so we forget about that one. With the field content of the standard model, you can also show that the theta term for SU2 is unphysical. It can be rotated away. So we also forget about that one. And so we are left with a single theta term, which is the QCD vacuum angle, which seems to be the only one that is physical in the standard model and seemingly tiny. Therefore, it's a CP problem. Abelian instantons, where the geometry really is sort of like asymptotic flat, otherwise R4, would turn this electromagnetic vacuum angle into a physical quantity. So these are beyond the contribution to the Axion potential. This is also just a practical, something of practical interest, I would say. Okay, so let me move on to the main topic of our paper. So just like for monopoles, having some field configuration that carries non-zero instanton number requires that there is enough topology somewhere for this instanton number to be supported. So typically the way that happens is in a couple of ways. So either when we have non-Abelian gauge groups, so typically we're used to saying that if we are in Euclidean R4, we need the third homotopy group of our vacuum manifold to be not trivial. And that's not possible for U1, so we need something like SUN in order to have monopoles. Another possibility is that the spacetime itself is topologically non-trivial. And here, for instance, the simplest example is something like a 4 torus, where if we have a 4 torus, we can wrap electric flags around one of the 2 torus and then magnetic flags around the other one, leading to a field configuration where also the integral of F is not zero. So this is of course true. It's not so useful if we live in this asymptotic flat space. There's no reason why we should go and sum over field configurations with this topology and this type of geometry in the path integral. So it's unclear to what extent that's actually practically important. The instantons that I'm going to discuss now, which share some similarities with some of the things that John talked about earlier, are Abelian instantons that do share some similarities with these two classes, but they are also somewhat different. And as we'll see, they are supported by monopole Bohr lines, and crucially, those Bohr lines are closed. Okay, so a very brief recap of some of the topological aspects of the Dirac monopole. So here is the Dirac monopole sitting at the origin. The field strength, so this creates a radial magnetic field. I can write the field strength in this way. If I integrate this field strength over a 2-sphere that surrounds this monopole, I get as an answer the magnetic charge of the monopole. Okay, and I'm setting G to be such that it's not here. So magnetic charge is quantized in units of 2 pi here. Okay. So as you know, it's always possible to write down F equals the exterior derivative of A locally, but not globally. So we can try choosing a vector potential like this. It will have some singular Dirac string, in this case along the positive z-axis. We can move the Dirac string around, put it maybe along the negative z-axis. These two configurations are related by a gauge transformation. This nevertheless allows us, as was done by Wu and Yang in 75, to define two different charts where we have a well-defined gauge field of which F is the exterior derivative. And that's okay, we can do that everywhere except at the origin where this monopole is sitting. Okay, A remains ill-defined here. So really, a U1 gauge theory that contains a Dirac monopole is not defined in all of R3, but only R3 with these points removed from the space. What if we now consider a loop of this Dirac monopole? Okay, again, in Euclidean space, So X4 would be like my Euclidean time direction, and I'm putting my monopole initially here in the X3 axis, and I'm choosing a gauge where my Dirac string is along this positive Z direction. As this monopole moves around its word line, the corresponding Dirac string is going to travel along this string warshed, which is a Dirac sheet of singularities. Okay. If I have a closed word line, as in this case, then all of this region, all of this two-dimensional region outside this disk would be a Dirac sheet in this case. Just like before, the position of this Dirac sheet is not physical. I can do a gauge transformation and move it to a region where the singularities live inside of the disk. So just like before, this allows me to define two charts to define my gauge field. And that allows me to define, again, a gauge field everywhere except on the monopole word line. So a U1 gauge theory that contains a closed monopole word line is not going to be defined on all of Euclidean R4, but rather R4 with, in this case, an S1 removed. Unlike R4 with a loop removed is now topologically non-trivial spacetime. This space has two boundaries. One of these is the spatial S3 at infinity that we're used to. But there's now also a second internal boundary, which is this S1 cross S2. Okay, so this is S1 cross S2. S1 is the word line S1. The S2 is sort of like an infinitesimal sphere that surrounds the monopole at every point along this word line. So I'm going to spoil the story for you first, and then I'll show you the calculation. So by construction, again, we've sort of our starting point was a field configuration with a Euclidean monopole. What that means is that if I integrate this F, the field strength, over this infinitesimal S2, this just gives me the magnetic charge that my monopole has. Okay, that is like the definition of what it means to have our Euclidean monopole.
Excuse me, in your consideration, you assume that the Dirac monopole exists in our world, right?
I'm assuming, yes, I'm assuming that there is such a thing as a Dirac monopole.
Yeah, but okay, well, you can take, of course, Polyakov monopole with M very large.
This... So we'll get to that in a second, yes. For now, I'm just treating this as a Dirac monopole because that's going to actually capture all of the relevant physics, in the effective field theory. But I'll get back to, you'll be completing the monopole.
But you would wind around. The topology appears when you wind around U1 type of topology appears when you wind around this contour, right?
Okay, so yes, so just having the monopole loop around is not enough to allow you to find the field configuration that carries Instanton number. If I also demand that the gauge field A winds around this word line, then it is possible to find field configurations where this integral is not zero. Okay, so now I'm just claiming this. So both, again, I need both that there is a monopole at every point in this loop, and also that the gauge field winds non-trivially around this monopole word line. So with these two things, I can now go on and compute this integral over HF. I've already chosen some smart coordinates that make this very explicit, but the bottom line is that these factors out in terms of these two quantities. One is the integral of F over this S2 times the integral of A over this word line. And so if these two things are quantized in units of 2 pi times an integer, then this thing is also going to be quantized in units of 8 pi squared. Okay. Yeah, and so the configurations with Instanton number plus and minus 1 would correspond to having n times n being either minus 1 or plus 1. So what these Abelian instantons correspond to, they correspond to sort of a Euclidean monopole loop that also has a twist, meaning that the gauge field has to also wind non-trivially around the monopole word line. Okay. You can also ask a little bit more. There are other ways to describe this field configuration. So again, before I turn on any of the winding, our monopole loop is a solution to Maxwell's equations with a magnetic current that is a delta function current localized on this loop. With winding, if we want to maintain our solution, if we want our solution to still be a solution to Maxwell's equations, it necessarily requires sort of some kind of electric current as well in order to be a solution. Okay. However, if we want the winding to be finite, this electric charge density cannot be a delta function localized charge density like for the monopole. Okay, you can show that this electric charge density has to diverge at most like 1/r as you get close to this core line. And interestingly, so this is a conclusion you can reach just by looking at the U1 effective theory and identifying these field configurations. This 1/r electric charge density is coincidentally also the electric charge density of the Julia C. Dyon in the BPS limit. Okay, but we haven't yet put any of the ingredients of the UV compression. At this level, this just arises as a requirement from the minding that this winding stays finite. And so what this effectively looks like from far away is sort of localized magnetic monopole loop, and then on top of that, some sort of like slightly sort of smeared electric charge on top of the monopole. You can also, it's actually also helpful to look at what this field configuration looks like far away. And you don't have to make any assumptions. You can just do sort of like the asymptotic multiple expansion and compute the components, the Abelian F mu components. So this is what F mu looks like far away. And if you look closely, this first term here in blue is precisely, in this case, the third isospin component of the non-Abelian gauge fields of the familiar sort of like BPSD instanton. And the second line here is the corresponding field strength, but for the anti-instanton. Okay. So yeah, well, if you require it to be self-dual, then you're gonna pick one or the other, and all of these various parameters are related to the winding and the magnetic charge. But yeah, so this shows you that already just by looking at these solutions, by looking at these field configurations purely in the effective theory, these Euclidean loops of Dyons with this twist look like one of the components of the non-Abelian, of the familiar non-Abelian instanton. You can also look at, try to compute the action of this instanton in the U1 picture. Obviously we don't know how to do this in a way that is simultaneously local and Lorentz invariant, but you can imagine there's a UV theory that you have that regulates the sort of singularity of the monopole, and you can sort of estimate the Euclidean action of this instanton, and it's going to have, the leading contribution is always going to be of the form 2πr, which is the length of this core line, times the monopole mass. Okay, what you learn from this also is that smaller values of R, so smaller loop radiuses, are going to have less action. So this solution actually wants to shrink. And if it shrinks so much that this quantity here is no longer large, you are no longer in the regime where you can trust your U1 effective theory. So you can identify and describe a lot about these Abelian instanton field configurations just in the effective theory. It seems like to understand how they actually contribute to path integral, with what exponential suppression they do, you do need to kind of invoke some type of UV completion. And so since I'm running a little bit low on time, I just mentioned you can construct a sort of UV completion of this field configuration that corresponds to a UV completion in the context of, for example, the Georgia-Glashow model. So what I'm writing just here is an ansatz for the Higgs, and also an ansatz for the gauge fields of OSV2. If I choose all of these functions to have the correct boundary conditions, both infinity and also where the magnetic charge is, you can convince yourself that this action, this ansatz corresponds to a field configuration that has finite action, which is what you want. And you can also convince yourself that it corresponds to, it lives in the sector with instanton number 1. Okay, so this is regular finite action field configuration with instanton number 1. And then in order to find the actual final details of the field configuration that actually solves the equations of motion, that's something that is now, at least this ansatz is now amenable to trying to answer that question numerically. And so this is sort of what the field configuration looks like. For example, this is the profile of the Higgs field. So this is the size of the Higgs field in various planes. So for example, this last image here is just in the plane of the loop after running the relaxation algorithm. And what you see is that indeed this thing sort of relaxes to a loop of, it's a Dyon loop where like the sort of the magnitude of the Higgs is 0 here, and then it quickly goes to its vacuum expectation value far away from this configuration. If you look in different planes, you see different things. What you see is that for every Euclidean time slice, there is always a Dyon and an anti-Dyon at every time. Okay, which is the crucial part, the crucial aspect why what allows these configurations to carry instanton number, but also carry, in this case, finite action. You can also look at the action of the field configuration, and as you can see, there's sort of a smaller and smaller radiuses. You can show that the Euclidean action asymptotes to precisely the action of the BPSD instanton in the BPS limit. So when lambda is equal to 0, which is equal to 8 pi squared over d squared. So this is just to say that numerically, we can show that this sort of, in the SU2 theory, at least, these field configurations are actually continuous deformations of the instantons that we know exist and survive when we have SU2 spontaneously broken to U1, okay? So yeah, so this is what I was just saying now. So as the radius becomes small, these Euclidean sort of Dyon loops approach the instanton configurations of the spontaneously broken of the Georgia-Glashow model. These are what we call sort of small, or sometimes we also call them like constrained instantons. The point here is, so before we spontaneously break SU2, this theory is obviously a scaling variant. There are instantons of all sizes that carry the same action. When we sort of Higgs the theory, naively, there are no longer solutions to the equations of motion that carry instanton. But of course, in the path integral, we are timing over everything, whether it solves the equations of motions or not. So we still have configurations with instanton numbers that contribute to the sum. And the way to capture that contribution, that again was developed by Affleck a long time ago, is in the context of these constrained instantons, where we sort of constrain the size of the instanton. In this case, would be the loop radius. And then, that allows you to see that they contribute as if they were stabilized at a size of order 1 over the BEF, okay, with this action. So it's sort of like the same story. My very last slide before the conclusion. So it's sort of fun. So far I've described how you can sort of identify and describe these field configurations in the U1 effective theory. The UV completion into SU2 is not very surprising. It's sort of something that you might have expected already. It also tells you that you shouldn't worry too much about contributions to the QCD axion potential because, when we think about the axion and the axion polarity problem, we already imagine the axion could couple to other non-abelian gauge fields, and there could be other instantons in there. And so this type of monopole loop contributions are really just the same field configuration. So, including both would be sort of like double counting. But the fact that you can identify these instantons in the U1 gauge theory also raises the question of whether there could be other QB completions of these abelian instantons that are just not the run-of-the-mill non-abelian gauge theory. So a fun possibility is, what if we take our Dirac monopole and we just turn it into a magnetically charged black hole? And this is something that is connected to some work that has been done before. So in fact, this type of Euclidean solutions featuring loops of magnetic charged black holes are also the bounds that describe the decay of a homogeneous magnetic field into pairs of magnetically charged black holes. Okay, so these solutions, and this was described by Strominger and also like Gary Horowitz and Steve Giddins and company a long time ago. So these solutions do not carry instanton number, but if we sort of extend these magnetic charged black holes and we make them Dyonic, you can show that there exist field configurations of just Einstein-Maxwell theory that do carry non-zero FHF, where the action seems to be finite and where crucially the asymptotic geometry of the configuration is R4. Okay, so again, from the point of view of summing over field configurations in the Euclidean path integral, when we have gravity, we should also be summing over geometries with Baryon topologies. But the boundary condition is that the geometry should remain flat. Okay, so claiming that something like a 4 torus can carry instanton number is not going to be very helpful because that's not going to go into the path integral. But something like this, where the geometry is asymptotically a 4, but there's an up topology somewhere to carry instanton number, this should go into the path. And so this is this black hole story is like work in collaboration with my student Elliot that we're working on. There are some subtleties, but it's another fun example to think about, and maybe there are others. So I'll leave it here. So just to summarize, defects in general, monopoles in particular, can have interesting and important implications for the standard model and beyond. Monopoles are a fun example because they are especially prevalent in many extensions of the standard model, and also really a standard model plus GR. And there are many interesting questions, especially when it comes to the phenomenological implications of these defects, still to be explored, as we also heard earlier from during John's talk. So yeah, thank you.
Right, good. So the question is, when you look at the Dyon loop from SU to UV completion picture, if I saw correctly, you said that the contribution is maximized at the scale F inverse, which is much smaller than MW inverse. On the other hand, the Dyon size, or so monopole size, will be of the order of MW to the inverse, right? So in one sense, I can even think about the Dyon loop at a smaller scale than its quantum wavelength.
I mean, so at some point, you shouldn't be thinking about them as like a Dyon loop. And it's just sort of like a single blob that looks more like your constraint instanton. But the point is that these two field configurations are really just continuous deformation.
So in this sense, within the MW size, right, which I cannot quite probe, but there can be quantum loop effect inside of that, and they can appear as instanton, Abelian instanton. Is that the picture that you have? Or?
Can you repeat this? Sorry.
So basically, we cannot probe any scale smaller than MW in principle that I cannot keep track of it. But inside of the blob of MW inverse,
right.
In principle, there can be quantum fluctuation inside of that, which can form a loop, which outside of the MW can appear as Abelian instantaneous. Is that the picture?
Yeah. I think that's basically what this calculation is.
Okay.
Again, we have a question. So to complete the calculation with the Axion dependence,
yeah,
you're using the Witten charge, but Callan showed that they are. But if you wanted to do it here, if we put in the Witten charge, wouldn't it be spread out over the size of the electron Compton wavelength because of disappearing Dyon story?
I don't think so, because the calculation I would do it. So I think the calculation here would take in detail it would be slightly different, right? What I would be doing is, so here's my Euclidean path integral, and I have, F mu, and then I also have I theta F with F. So I'm summing over various field configurations, but now when I sum over theta F with F, I know what the field configurations are that give me that F with F quantized. So that's just gonna give me, it would just give me like a cosine potential that depends on theta.
But I think Callan is saying there's vacuum polarization effects that make it much more subtle.
This is all Euclidean though. So this is still a good solution to the equations of motion, at least in order in the semi-classical expansion. You could include, quantum corrections to that and try to compute like the one with determinant to see what that looks like. I think the fact that this is Euclidean is actually not an unimportant difference.
He's saying there's electron loops that are not suppressed because they also have magnetic couplings in them. But let's talk about it later.
So in this time, we should thank the party.
Oh, super.
No, we are not affected by that. That's good. That's good. So that's not common.
I was concerned on Brennan guy and Baer. His was the only one that seemed like maybe there was something.
So I'll do this.
Yes.
Yeah. I don't know.
Some of them.
Okay, great. Welcome back to the second day of the afternoon session. First, we already have in-house Anson book from Baer to give us talk on predicting dark matter Baryon abundance ratio. Anson, please. Yeah, thanks. So thanks for having me. So today I'm going to be talking about predicting the dark matter Baryon abundance ratio. And so, like all models, you either if you buy it, you don't give it back. So this is work done with former student and current postdoc. Okay, so at this point, I think everyone knows we know so little about dark matter, we can fit everything on we know about it on one slide, which is that it's non-relativistic, so it fits inside a galaxy, it has gravitational interactions, that's how we find it. Depending on who you ask for, there's no at least conclusive evidence of other interactions other than gravity. Its perturbations are all adiabatic, not iso-curvature. And the last is that its energy density right now is about 10 millieV to the fourth. However, of all of these, you should immediately look at this and be like, well, that's crap. Why? Because it is both time dependent. So if you think this value is special, just wait a few years or something and then it'll change. And it has units, and this is one of the first things we learn in physics. Anything with units means absolutely nothing, right? The whole thing of saying it's 5 meters just means that it's 5 times as long as a meter span. Units, you should not talk about anything that has units. Everything should be dimensionless. And so of these 5 things we know about dark matter, the 5th one is not really information. We'll have solved this problem. And this is why whenever you hear people talk about these energy densities, they phrase it in terms of the ratio between the energy density in dark matter to the energy density in baryons. And when you do this, you get a number 5.36. At least this is the 2018 value. And this solves all the problems. This is no longer a time-dependent thing, at least up to timescales of about a KD or so. These redshift exactly the same. It has no units. All nice and good. And so this is something you can take seriously. And you can tell I'm taking it seriously because I included decimal points. Something you never see theorists do unless they're being very serious. And this is a very surprising number, 5 here, if you think about it for a little bit. So why is it surprising? To understand why it's surprising, we go back 100-odd years to the golden age of physics. And a bunch of old famous people back then said, well, there's a question that they are very confused about, which is why is the proton mass 18 orders of magnitude lighter than the Planck scale? And of course, if you're like me, you hear famous people tell you things and you ignore them, right? This is how we got into the field. We ignored our betters and said we're doing this regardless of how little money we make. And it turns out that actually, all evidence to the contrary, this turned out to be a good question to ask. The reason why it's a good question to ask is because nature decided to solve it, right? The ultimate arbiter for physicists is nature, and nature decided to solve this problem by very elegantly relating the proton mass to the Planck scale by dimensional transmutation. In other words, an exponential of some order 1 numbers. And so we shouldn't be saying, oh, 18 orders of magnitude difference, we should be taking the log of that and be like, oh, this is 20. 20 doesn't really need explanation. It's an order 1 number, close enough. And so that's why this 5 is so surprising, is because if you then look at the baryon mass, it is, or the total energy density in baryons, it is also exponentially dependent on order 1 numbers. And so this thing has exponential sensitivity, shouldn't be anywhere close to anything else. And if you look at this, 5 does not look like an exponential number, right? This does not look like 10 to the 18. This looks like order 1. And so this really, to me, just says we know so little about dark matter that this sort of coincidence really needs to be explained somehow or another. You need to at least have an opinion about it. Okay, so of course, I'm not the first to talk about any of this. I'm sure everyone in some sense has heard versions of what I just said before. And there's basically only one type of solution that's really talked about these days. And the idea behind it is that we have 2 energy densities that are about the same, dark matter and baryons. And so people notice, well, this is m times number density, n times number density. Easiest way to get them both about the same is to make the number density of dark matter and baryons about the same, and dark matter and the masses about the same. And there are a whole plethora of different ways of doing this. They have names, and hundreds of papers have been written about them. Originally, the idea was just being like, well, way back when dark matter was so poorly understood, it could have been a copy of us. And so they started off talking about mirror world, where dark matter is just a copy of us. Copy with about the same mass, about the same number density. Great. Turns out, these days, if you want, you can still get these things to work. You have to work a little bit harder, but it's still a viable solution. Other ways of doing things are asymmetric dark matter, which is you just produce a bunch of baryons and then convert, like, order half of them into dark matter, and then you have number density is the same. Explaining the mass is the same are a little bit harder because of the exponential and the baryons. There have been different approaches using CFTs and unification and whatnot. I'm using sociological fact. About 700 odd plus papers on asymmetric dark matter, about 10 papers on all of this side. So I found that quite amusing. But that's sociology for you.
And what about anthropics? Is there an anthropic reason? Oh.
I haven't comments about this entire thing. But if you want, I can comment about it later.
Okay.
Yeah.
Sonny, are you a plant? Is that a plant?
Okay, just checking. He's really just checking people are paying attention to my notes. Okay, so the question is, if that's the only solution on the market, then, or basically, is everyone being stupid looking for axions? If you say we have to take this seriously and dark matter has to be of order GeV, then are we basically hosed? Do we just look for GeV scale physics and that's about it, or GeV scale dark matter? And yeah, sometimes I like other dark matter candidates. And so it would be nice if they at least have an alternative that works for other models. So I'm going to get into the details later, but the sketch of the idea is very simple, which is somehow create baryons, somehow create dark matter. They're going to be very different energy densities, exponentially different. And couple of moduli to the mass of the baryons and to the mass of dark matter, such that when you just let this guy evolve in time, it'll minimize its finite density potential and just bring these two guys together. That's going to be the idea. And I'll get to it in a moment. But first, I'm going to also be a little bit more explicit about what I'm choosing for dark matter. I don't need to be, but if I want to actually literally predict the baryon to dark matter ratio, then I'm going to have to actually specify what dark matter is.
Is there a particular reason rho dark matter is hierarchically smaller than baryons and not flipped?
This is going to happen because this relaxation mechanism will only work when it's not relativistic. And it turns out to be very easy to make heavy baryons non-relativistic. And if it was reversed, it'd be making a very light baryon non-relativistic, which is just harder. So in practice, if we lived in a different universe, it could have been scrambled completely different. Given what we know, this hierarchy turned out to be, or this ordering turned out to be easier. Yeah. Okay, so let's specify dark matter. I am somewhat embarrassed to admit that the dark matter candidate I'm going to choose is the QCD Axion. Everyone loves it and hates it at the same time. I'm basically not going to care anything about the Axion except for this one equation here, which is the mass of dark matter will be essentially proportional to the QCD scale to the 3/2 over FA. That's really all I care about of the QCD Axion. It depends on FA and it depends on the QCD scale. Okay, great.
We do get the 3/2 form.
It's because when you say it's proportional to m pi times f pi, the mass of the pions depends on both the mass of the quarks and the mass of QCD, and it comes from m pi's. Yeah. Okay. Which does mean just like in practice, I'm not going to take the QCD scale that much above the Higgs Fed so that I don't start screwing around with the quark masses too much, just for simplicity. Okay. So I'm actually going to go one step farther and tell you the UV completion of the Axion. It'll become a little bit more clear why later. But the UV completion I'm going to consider is basically the composite Axion. The reason for this is I'm a bit of a pessimist. If we find something new, I expect it to be a copy of something we've seen before. And we've seen Axion-like particles before, namely the pion, for example. And these were composite objects from QCD. And so if we see another Axion-like particle, or maybe the Axion, then it's probably also the composite pion of some other composite theory. And so this is Jimmy Kim's original composite Axion. I think if you don't care about the quality problem, it is the simplest composite Axion model you can write. SUN confines can give you one light particle, which is the QCD Axion. Okay, but that's all I want out of that. Okay, so for the rest of the talk, I'm going to take these two ideas and mash them together. In particular, I'm going to take the QCD Axion, dark matter, and then actually flesh out this idea of trying to relax the energy densities be equal to each other. And you'll find some fun, somewhat surprising facts, at least to me, that this actually, for example, just gives you a prediction for what the two ratios are equal to. Okay, all right, rather maybe a post-diction and then predicting more decimal points. Okay, so how do let's actually specify this thing here. And so it turns out to get this to work, I only need to do one thing. I'm going to add one new particle, phi, and one new coupling, which is I'm going to couple it to the confining sector that gives the Axion. In particular, this thing is a moduli for FA. That's really all I'm doing. One particle, one coupling. And this changes when the confinement scale of SUN is. And so you can relate, for example, FA, or the confinement scale of FA, to the gauge coupling of this guy, or equivalently to the scalar of phi. Main point is just that it's exponentially dependent on phi. The exponential is not even important. It just makes doing things like taking derivatives easier. So this is what it means just to be a moduli for FA. If people, I guess most of the people here have done a lot of SUSY, so they'll recognize equations like this, but if you haven't, it's a fun thing to go through. Great. So it's a moduli for FA, which actually also means it's a moduli for QCD. The reason for this is when this sector confines, right, the QCD Axion talks to QCD. So changing the QCD Axion also changes QCD. In particular, you'll notice when this guy confines, it removes a bunch of colored particles. And so that changes the beta function of QCD. And in particular, you can just calculate, go through a little bit of math. calculate how does this thing act like a moduli both for QCD and for FA at the same time. And in fact, how much of a moduli it is for FA and how much of a moduli it is for QCD is just related to each other by beta functions. That's it. Okay. We now have enough information to do the one line of math to see how we get the prediction. Yeah.
Shouldn't you also have a similar coupling phi with G mu of QCD?
Yes. So you could say
it will be generated. No?
It is generated by this. When you integrate out in particular, when you write the one loop beta function for QCD, it depends on the masses of some of these quarks or when they get integrated out, or rather the scale FA. And so, yes.
No, but just at the loop level, you generate also an operator phi G mu QCD squared, right? So you also
you need to go through more than just one loop, but yes.
Huh? Yeah, but it's a strongly coupled sector, so those loops are not suppressed.
And so in some sense, this beta function is the leading order way of doing it. But there are going to be other effects, yeah. I mean, for example, you could just say
which could be equally broad.
Yes. So this is going to be the leading order thing, because another way to get this is looking at just saying everything else is massless and don't pay attention for a while. This thing is some confining sector. This and we know basically by conformal symmetry how it changes everything else, in which to leading order in FA is going to be the same expression. But yeah. Yeah, so there are going to be tons of also finite threshold corrections and whatnot as well.
Just to make sure that the phi's and chi's are massless fermions.
These, to get the QCD axion, they are massless, which is why this is not the best way of solving the axion quality problem. So this is, if you just want the composite axion, this is what you would write down. If you wanted to also solve the quality problem, you might try to go beyond this.
Yeah, just to make sure how many quality problems, sorry, how many strong TP problems have.
Yeah.
I have two sectors, but I think one is automatic solve.
Yep. So the strong CPU problem is essentially gets reconstrained to why are the masses small.
But typically solutions would introduce a lot more matter, right? So would
yes, which would just, from this point of view, it just changes beta functions.
Exactly. Yeah, but does it change it in the right direction?
We'll see. Yeah. So the idea is this thing's a moduli for dark matter. It has some coupling exponential in your scalar. It is also a moduli for QCD. In particular, it is forced to be a moduli for QCD. So in particular, this coupling is predicted. And so if you take the finite density potential, mass times the number density plus mass times the number density, solve for the minimum. Take V prime equals 0. I can take derivatives of exponentials. It pulls down a C dark in front of the dark matter, C baryon in front of the baryons, and the minus sign will be important. And what you find is that when these guys are equal to some beta functionality times rho dark matter minus some beta functionality times rho baryons is 0, or the ratio of these two is just the ratio of some beta functions. In particular, for this particular model, it's this guy here.
It's a one loop result?
This is a one loop result.
Yeah.
Yeah. And so regardless of how you produce dark matter, how you produce baryons, you will eventually relax your proton mass to dark matter mass to give you a ratio of energy densities equal to this. Okay. So you now arrive at the point that I found amusing and why I sort of ended up pursuing this, which is you can put n equals 2, 3, 4, 5, 6, 7, 8. And sort of you just get some random numbers. Turns out the observed value of 5.36 is a percent level measured thing. And that's this dark green line here. And by chance, the number for 8 gives you 5.33 within the 1 sigma error bars. Now, like any skeptical person, you should be like, okay, that's great. Should I start putting, what are the real error bars for everything? As mentioned before, this is a one loop result, so it'll change. I would just conservatively give it some 10% type error bars. What are the corrections to one beta functions? I'll just say 10% for now. The point will give you percent level error bars, but of course, you shouldn't necessarily trust them because they make lots of assumptions. They assume standard cosmology, so no ineffective. There are already facts that like H0 issues, which are 10% problems. So personally, I look at all this and be like, well, we clearly don't understand cosmology and really at the 10% level. So probably the error bars are closer to 10%. But of course, you have to sort of marginalize over all your different types of theories that you personally find reasonable, et cetera, et cetera. But personally, I think these are probably error bars closer to 10%, which are like here. So the fact that they match within percent level is cute, but I would just say that's all it is. And yes, I would have been, if the simplest model didn't work, I would have started throwing in tons of crap. But it turns out literally the first models of composite Axion work. That was literally Jenny Kim's first model. And so, yeah, I was surprised I didn't need to play more games. Okay. So let's very briefly talk about what the cosmology of this looks like, what the relaxation phase looks like. In particular, you can just solve the equation of motion for phi, put it in some background, see how it goes. You can even do it fairly analytically, but no one has the time for that. So let me just tell you the answer. So at early times, when its mass is less than Hubble, it freezes out. Nothing is changing. Lambda QCD is not changing as a function of time. The moduli is frozen. At late times, you find the finite density minimum. You just oscillate around the minimum. It decays away. Energy actually decays away quite fast. This middle part is the part of the relaxation phase. And you'll notice, for example, that it is not oscillating. It's a monotonic decrease. And so just go through a little bit of math. What you find is basically during this phase, mass is actually equal to Hubble. Kind of amusing that this ends up being just a critically damped harmonic oscillator. The mass falls like 1 over the scale factor. I guess this is the solution of what things look like in a radiation-dominated universe. If the mass is falling like scale factor, this means the dark baryon energy is falling away like radiation. And also amusingly, the kinetic energy of your moduli happens to be half that of the baryon. So it's another thing that just might be order 1 of the energy density. Okay, so before going on, I have another 5 minutes or so. I'm going to remind people of the Trojan War. And so what happened in the Trojan War? Helen, the most beautiful woman in the world, went to Troy, and the Greeks were not particularly happy about this. And so in pursuit of beauty, they just burned the city to the ground, killed many, many people. So how does this have to do with any of us?
That's the shortest retelling of that.
I have only half an hour. As fast. And so why did I bring this up? I find this extremely cute. And so I will go commit great model building violence to get this prediction to work. So I will take many models, throw them onto a pyre, and then see which one ends up being fireproof. So why do I have to bring this up? This model, if you decide to make it the standard model, only has one small problem. It turns out to be very excluded. However, no one's ever let that stop them before. So I'm not gonna stop. I'm going to just see what it is that's excluded and fix these issues. It turns out all of our measurements that exclude this are late time measurements, whereas the solution is an early time relaxation thing. So it factorizes quite nicely in that you can solve these problems independently of the relaxation mechanism I mentioned before. So the 2 problems are 1, fifth force searches. I have a massless moduli, and its coupling is going to have to be stronger than M Planck. And we know fifth forces at all length scales, if there's no mass to it, then mass dependence, then you're very screwed. The other are temperature-based effects. which I'll explain after the first one. But okay, so how do you get around fifth forces? Anyone who's thought about fifth forces know the answer, which is the bounds disappear exponentially fast with mass. So just give the damn thing a mass. And so that's what we do. We say people who thought too carefully would have complained that I didn't even put a mass to begin with. So now I'm going to put in a mass. In particular, I'm just going to put some cosine with some wiggles. And so how does this solve the problem? At early times, the Baryon asymmetry is very large. And so this cosine wiggle doesn't matter because rho baryon is huge. It's larger than any GeV scale to the fourth potential I decide to put for this guy. And so it oscillates around, finds its right minimum, gives a 5.33. Then as the universe cools down and the baryon density gets lower and lower and lower, these wiggles become important. Wiggles get developed. You fall into the nearest minimum. And late times today, when their measurements are made, it has a mass now. And so you get around current constraints. So that's the idea. Just add up some wiggles. Here, I guess I added a lot of wiggles, but you can add less if you want. Okay, so that's one. The second is temperature-based effects. So one of the amazing things about QFT is that it does everything that's allowed. So in particular, I added a moduli for FA. It became a moduli for QCD, but it also becomes a moduli for every other damn thing in the world, right? At loop level. And so that means even though I wanted just to have that finite density potential, it's going to pick up a whole other number of things. An example is that it can become a moduli of alpha E and M, also with basically the order 1 coefficients. It's not really that suppressed. So if you go through and do the world's simplest two-loop diagram, because it's a two-loop diagram that turns into a one-loop diagram squared. If you've never done thermal field theory calculations, there are two-loop and three-loop diagrams that just factorize into one-loop squared or three-loop squared after a momentum redefinition. And so you get great bragging rights with zero work. But you can just calculate how much does the free energy depend on alpha, and you get some 10 to the minus 6 type number. And you're like, well, 10 to the minus 6, that's really small, right? Yes, it's small, but 10 to the minus 9 number densities of baryons are even smaller. And so if you just take standard cosmology and ask, when do the baryons become more important than everything else in the standard model, like the dependence on alpha? Turns out it's about when the temperature is about MeV. So at temperature of MeV, you're not going to want to be relaxing the proton mass from a TeV to a GeV, right? You're going to be very excluded. So that's the problem, which is you wanted it to be a moduli for QCD, and it ended up being a moduli for everything else and had issues. Great. So let me just say the solution. The solution is to take the coward's way out and do an entropy dump. If you do an entropy dump, you can make sure the temperature doesn't grow very fast, but the energy density in baryons goes up. Okay, so history, but I'm out of time. So the claim is jump through a bunch of hoops, stand on your head a bit, you can get things to work. And so to conclude, I think the baryon dark matter coincidence is a troubling problem. We know so little about dark matter, you should at least have an opinion on it. Your opinion could be that it's an accident, fine, but you should have an opinion on it. And what I was proposing is just a different way to solve this problem, which is to have a scalar, a moduli, that adjusts the dark matter and baryon masses until the energy densities are equal. It has some fun things, like, for example, the baryon proton mass will be dark matter density dependent and things like that. I didn't describe it, but it can actually apply to pretty much all models of dark matter. And I'm in the weird situation where I now start caring about decimal points. Even if they end up getting the right answer, I still won't believe it, but I at least pay attention now. All right, thanks.
Could you tell us about the history that you didn't have time to tell us about?
Yeah, so very quickly, after inflation ends, you decay into whatever gives you the entropy dump. because I have an entropy dump, I have to really crank up baryogenesis. Affleck-Dyn complained about that they produce too many baryons, and so just use Affleck-Dyn. It's a non-thermal mechanism, and so I don't even need the universe reheated to do baryogenesis a la Affleck-Dyn. Then you do the relaxation thing I mentioned before. Misalignment mechanism for dark matter works just fine. After relaxation ends, the wiggles become important and you just nail everything in place. And then you just have standard cosmology. And you can go through, specify some of these models, but that's the basic history that you have to go through.
I'm sorry. So you made this comment earlier that the exponential dependence of the moduli is not important, really?
Yeah, that's right.
Well, I'm wondering for the dynamics, is it like in the sense that if I had like a power law dependence, can I still scan parameter space fast enough?
Yeah, so the exponential is nice in that it takes the problem you had, which is exponentially sensitive. It means it's exponentially easy to change the mass. When you have linear things, you just need to have a huge range of field values for the scalar, which fine, but it's like, I literally wrote there, but you could do the same thing in supersymmetric theories with like Higgs type mechanisms. If the proton mass came from a Higgs mechanism, you could write something analogous. That's not a dimensional transmutation like this one, but just you follow a couple of versions.
But you have like enough time, like if you need to scale it really far.
So, great. I don't know if I haven't looked at the other example I know in detail that much. So I don't know if the baryon density falls like 1/A or does it oscillate or not. So I guess the answer is I don't quite know. Easy enough to find out.
So just coming back, so is there do you think there is a plausible anthropic solution for this number or not? Just I guess we're running out of.
I personally don't think so, but that's partially because I don't feel comfortable extrapolating the one data point of life to saying we know everything about life. And two, all the anthropic arguments I know of are like give you like 3 orders of magnitude to play with. And so then why are you not 10 to the 3 rather than 5?
Okay. No further questions? That's good.
Less. Yeah, the reason it's not diluted is because there is.
Next, we're happy to have Baer from University of Oklahoma tell us about Axion dark matter from SUSY.
Okay, I'm pleased to be here. We actually started on this vein of work on a sabbatical at Minnesota back in 2014. So this work is inspired by Weinberg. He mentions in his History of Science book that the appearance of fine tuning in a scientific theory is like a cry of distress from nature complaining that something needs to be better explained, i.e. if your model is fine-tuned, you probably have something wrong. And Einstein says everything should be as simple as possible, but not simpler. And I take that to mean that further we stray from the standard model, the more likely we are to be wrong. So today I want to talk about all Axion dark matter from supersymmetry. And this material is embedded in these 2 papers, one which actually just came out this morning. Okay, and it develops what's called a WIMP quality problem, to go along with the Axion quality problem. So we've seen so far from the LHC that the standard model rules at energy scales around 1 to 200 GeV. But nevertheless, it's hardly the end of the story since the standard model is beset by these several fine-tuning problems, the H hierarchy problem, the strong CP problem, and the cosmological constant problem. And the most plausible solutions to date, at least in my mind, so far for the gauge hierarchy problem, you need supersymmetry to stabilize the hierarchy. For the strong CP problem, we need the Axion. And cosmological constant problem, the only viable solution so far is anthropic vacuous selection from the multiverse and then string vacua. So we'll find that some of these solutions affect the phenomenology in a profound way. But first I have to, I'm here at Minnesota, and I have to explain why I'm still doing supersymmetry. And the reason I'm still doing supersymmetry phenomenology is that we believe in the 20th century, the calculations of fine-tuning overestimated fine-tuning in SUSY models by factors of 10 to 10 to the 4. And that's actually for another talk, but there's plenty of natural parameter space in some supersymmetry models. Others get ruled out if you use a more model independent and conservative measure called delta electra weak, which basically compares the weak scale contributions from supersymmetry to the Z boson mass. And the fundamental implication of this is that you get lytic xenos out as a signature of naturalness. And there'll be some more talks on lytic xenos tomorrow. Another reason I keep working on this is that there was a third string revolution from 2001 to 2004. You don't speak of too many revolutions because it gets sort of odd, but this was the emergence of the string landscape. And people usually think, well, anthropic selection from the landscape is non-predictive. But Mike Douglas proposed that you can actually make statistical predictions from the landscape, and he and Susskind and Arkani Ahmed and Katrin Demopoulos argued rather generally that the landscape favors large soft terms, but they have to be tempered by the weak scale lying within the Agrawal, Baer, Donahue, Seckel window, i.e. the derived value of the weak scale should not be too big or too small, because otherwise atoms won't form, complex nuclei, and hence atoms wouldn't form in our particular pocket universe. If you look at do statistical scans that favor large soft terms along with this window, then it actually predicts that the Higgs should be around 125 GeV, with sparticles typically beyond present LHC reach. This is what Douglas calls stringy naturalness. And the signature of this is that LHC might be able to dig out difficult lytic xeno pair production signal in the coming years. And there seems to be some 2 sigma excesses in the soft dilepton channel. And so for this material, there's a recent review article here that covers that material. But today's talk, I'm going to talk about a new theory of natural SUSY dark matter, which ends up being all SUSY DFSE axions. So if you go back and read the old literature, here's a paper by Arkani Ahmed and Demopoulos on split supersymmetry with over 1,000 citations. They cite the main successes of SUSY solving the gauge hierarchy problem consistent with gauge coupling unification, and it predicts a dark matter candidate. And then they go ahead and say, well, let's preserve these latter 2 predictions, but throw away the first one in lieu of landscape selection. And so from this point of view, supersymmetry predicts a dark matter candidate, and I think they had in mind the lightest neutrino. But here I'm going to argue that actually, from more general considerations, the SUSY dark matter candidate should be the Axion, and it emerges from solving fundamental problems in the MSSM. So that's the topic of today's talk. And so if we want to go ahead and construct the MSSM, we start with the standard model gauge symmetry. elevate the fields to superfields, add in an extra Higgs doublet, and then impose an R parity conserving superpotential, and we add all soft supersymmetry breaking terms. It's a well-known recipe. Steve Martin's got out a new book on it. And here is the R parity conserving superpotential, including neutrino mass terms. Now, one problem is that you've got more superpotential terms that people usually set to 0 by imposing an ad hoc R parity conservation. And so these allowed terms all get set to 0. If they weren't set to 0, then products of these R parity violating couplings would lead to rapid proton decay. And so the products are that these two couplings should be less than 10 to the negative 25. Of additional concern is that there's possible non-renormalizable dimension 5 non-renormalizable operators that also lead to proton decay unless these kappa terms are suppressed at the level of 10 to the minus 7. And up here on the first line, there's another problem that people usually don't address, and that's the so-called mu problem, namely that the superpotential has a mass parameter mu in it, and it's supersymmetry conserving and not supersymmetry breaking. And so you'd expect it to be up at the Planck scale and not at the weak scale. But phenomenology really needs the mu parameter to be down at the weak scale. So first of all, we want to go ahead and solve the mu problem some way. And there's actually 2 steps to solving the mu problem. First, you have to go ahead and forbid it and get rid of it so it's not up at the Planck scale. And then number 2, you have to go back and regenerate it back around the weak scale. So that's one problem with this model. Another problem, of course, I mentioned is just the ad hoc R parity conservation, which is imposed just phenomenologically. And the other one is that these kappas, you'd like to have a reason that they're so teensy. So putting it all together, you'd realize that constructing the MSSM is actually missing some fundamental ingredient that might be important for phenomenology. So instead of going with R parity conservation, one method to make it more palatable is to try to implement instead discrete gauge symmetries. And this was begun, I think, well, back around 1991 by Ibanez and Ross. These things, if you construct the right ones, they can forbid the R parity violating terms, but they do not forbid the mu parameter. They're discrete gauge symmetries, and the gauges come in with opposite gauge quantum numbers. So they don't forbid the mu parameter, and nor do they forbid the dimension 5 kappa terms. An alternative is instead to try to implement discrete R symmetries. These R symmetries are intrinsically quantum or symmetric quantum symmetries where the superspace coordinates have R charge +1, E theta is R charge -1, and the Lagrangian is integral d2 theta w. So the superpotential has R charge +2. These things are more palatable because they actually arise as discrete remnants of string space-time compactifications and have been derived in many orbifold compactifications, for instance. So they seem to be well motivated for solving problems like these. So the heroes of this story are these people here. Me, Brady, Ratz, Ross, Kieran, Mittelberg, and Voderban in this paper from 2011. They categorized all the discrete R symmetries, which are anomaly free up to a universal Green-Schwarz contribution. They allow all the Yukawa terms in the superpotential, which you want to have in there, they allow the neutrino terms, so you can develop neutrino masses. They forbid the R parity violating terms. They forbid the mu term, and they forbid the dimension 5 proton decay contributions. And the R charge assignments of the standard model fields are all consistent with SU5 or SO10 grand unified symmetry. So you'd think that they wouldn't muck up any of the gauge coupling unification. So the charges, the discrete R symmetries that they found that do all these great things are Z4R, Z6R, Z8R, Z12R, and Z24R. And in particular, the Z4R is consistent with SO10 weights, the others with SU5 unification. So by imposing the discrete R symmetry, we can do all those wonderful things. And you can work out for the anomaly cancellation what the relative R charges are of the standard model fields. Remember, the superpotential has to have R charge 2. So obviously these Higgses, when you put them together, are all forbidden. That's forbidding the mu term. But then the other R charges combined with the Higgses give you the proper Yukawa couplings. So we know what the R charges have to be, but then we have to also regenerate the mu term. And we do that by introducing two H singlet superfields called X and Y that couple with the MSSM so that the superpotential will actually contain HUHD, either XY or X squared or Y squared. Steve Martin labels these as 4 base models. The author's initials are listed in here if you want to find out who came up with each of these models. But the HUHD superpotential terms, if these X and Y fields develop beds, then these terms will turn into a mu parameter, and these terms help stabilize the scalar PQ part of the potential. And then we can regenerate the mu term via Tim Millis' original solution to the mu problem from 1983, where the mu term originates out of the superpotential. Okay, now very important for this procedure is that our revised MSSM, now you can go back and check, that has a accidental Lobo U1 PQ symmetry. Here are the PQ charges from Batrolo and Martin. If you go back and plug in all these charges, you find that all the remaining terms, along with the X and Y fields, they would have PQ charges labeled over here for these 4 different base models. Then we've actually got a accidental global U1 PQ symmetry. The axion is going to lie in a linear combination of the X and Y fields. And so spontaneous U1 PQ breaking is going to generate a axion, pseudo Goldstone boson, which is available to solve the strong CP problem. And in fact, for the higher CNR symmetries, we can actually solve the axion quality problem as well by suppressing higher dimensional operators that would displace the minimum of the PQ potential. Okay, and some of the work on this issue is listed in these papers here.
So what do you mean by the strong enough ZNR? I thought you already visited and exhausted the good list of discrete symmetries of R parties.
What was the question?
So what is the strong enough ZNR symmetry you are going to?
Well, you get higher dimensional operators that can displace the minimum.
I understand that quality problem, but earlier you already said people revisited all the discrete symmetries with R parity that satisfy all the good properties.
Yeah.
Here you mean I impose an additional.
Well, I'm saying I put this in parentheses. That's an ancillary topic to explore if people are interested. But here I'm going to focus on a different thrust.
Okay. Also, you have 10 minutes left.
10 minutes? Okay. So we go ahead and take that PQ potential and calculate the SUSY conserving part of it and the SUSY breaking part of it. You see factors of Planck are entering into it. With this sort of a scalar potential, you can map it out in the phi x versus phi y space, and you find it actually develops a minimum at an intermediate scale around 10 to the 11 GeV. So these two fields, the x's and y's, get 10 to the 11 intermediate scale devs. That's just right for generating, say, 10 to the 11 squared over m Planck. Gives us a weak scale value of the mu parameter. That's basically Yukawa coupling times the PQ scale squared over m Planck. And the difference of this with Giudice-Massiero is that Giudice-Massiero wants to develop a mu parameter of order of the soft terms. This one develops one where the PQ scale, which need not be the exact same as the SUSY breaking scale, can be quite a bit lighter and in accord with electroweak naturalness where you get light xenos. And even though the soft terms are quite a bit heavier. This is the parameter space. If you have large enough A sub F soft terms, then you can generate mu parameters of around 200 GeV for these different Yukawa couplings. And so it all works out quite nicely. And so we've solved the mu problem. And the needed MSSM terms are allowed. R parity violation is forbidden. So we've got an accidental R parity conservation as well. Dimension 5 proton decay is forbidden. And then you'd expect the dark matter to be a mixture of axions and WIMPs. Okay. And to check this all out, we've actually got 4 different base models, 5 different discrete symmetries. And then under these discrete symmetries, there's various possible R charges of the X and Y fields that give rise to a mu parameter around the weak scale. And all total, there's 54 possible models that can do this sort of thing. And so once you've got those models, now these forbidden operators actually can reemerge because we can couple, this is for instance a trilinear R parity violating operator. It can couple with the X and the Y fields with different powers and suppressed by m Planck to the p+2 power. Then if the X and Y fields develop VEVs of order to the Peche-Quinn scale, we're going to regenerate the R parity violating and proton decay operators, albeit suppressed by powers of the Peche-Quinn scale or the Planck scale. So here are the R charges of these various R violating terms. So we can go ahead and concoct, put enough X and Y fields in there with their appropriate charges to regenerate these guys. The Weinberg operator already works. It's already at +2. So that's allowed. And these other things can be regenerated, but suppressed by FA over m Planck to the power n. And so both U1 PQ and R parity emerge as accidental approximate symmetries. And in this case, since R parity conservation is now approximate, the light of SUSY particle is unstable and should decay. As an example, here's the B2 model with the R parity violating terms. Several of these give FA over m Planck suppression that we expect is a factor of 10 to the -7. You get some cubic ones which give you far more suppression. These ones would lead to an LSP with a lifetime bigger than the age of the universe. And then the dimension 5 proton decay operators are not forbidden, but they're highly suppressed. This is the case of the B3 model. Again, it's got some of these FA over M Planck, and in this case, the bilinear terms are also suppressed. So everything looks pretty good from that point of view. An important point is that for the cases where R parity violation is suppressed at the level of 10 to the -7, then you're actually going to produce the lightest SUSY particles in the early universe as usual, but then their lifetime is such that they can decay before Big Bang nucleosynthesis and after neutralino freeze out. And so this sort of suppression is not enough to fulfill proton decay bounds. So you still will need some extra handle from discrete gauge symmetries, perhaps baryon or lepton priality or proton hexality, but that will forbid some of these R violating operators, but not others. We'd expect, in this case, a suppression of 10 to the -7. In that case, the WIMPs all decay away, leaving only Axion dark matter. Here's a plot of the lifetime of the lightest neutralino versus the R parity violating couplings. If they're at the level of 10 to the -2, 10 to the -3, the LSP will decay in the LHC detector, and you'd probably see these guys with delayed decays. If they decay way back here, they might decay into distinctive signatures without too much of a delay. But if you start getting up into this regime here, below 10 to the -4, and FA over M Planck lives around here, then you got this broad region where you can decay between neutralino freeze out and Big Bang nucleosynthesis. And then you get all Axion dark matter. If the couplings are even smaller with gross suppression of FA over M Planck cubed, then you'd live longer than the age of the universe, and you'd be susceptible to the present bounds. Now the question is, where are the WIMPs? And it hasn't been mentioned yet at this conference, but in October, the LZ experiment came out with strong new bounds from WIMP searches that improved by about a factor of 4 or 5 over previous bounds. And so the latest direct detection bounds from LZ 2024, they still have no signal. It's this red line here. Here's a plethora of supersymmetric models. These ones are where natural supersymmetry lies, and some of these with low naturalness measure would likely be ruled out on the basis of, even with a depleted abundance of WIMP, this C factor here is a fractional WIMP abundance, where it's mostly Axion dark matter, but even with a depleted WIMP abundance, you could still be ruled out. So the LZ 2024 is consistent with the case of all Axion dark matter, where these WIMPs would decay away in the early universe. And then the question is, if you're not going to see anything at WIMP detection experiments, how about Axion detection experiments? Well, the MSSM, augmented by these X and Y fields, leads to the supersymmetric DFSD Axion model. And then when you compute the Axion photon-photon coupling, you have to include the matter fermions, but also now the Higgs-zenos. And the Higgs-zenos come in with a negative PQ charge here, and you get almost a complete cancellation in the terms of the Axion coupling. Matter of fact, for M up over M down equal to 1/2, I think you get complete cancellation. And so the coupling is highly suppressed from what you usually see on these plots, and well below the current experimental limits from ADMX. So you expect to live along this line here. These dots are from a depleted abundance. If you got 100% abundance, then you'd live along the brown line there. Okay, and then the last thing I'll say, since time is drawing nigh, if this is a natural supersymmetry, then we're going to be making Higgsino pair production at a rather large rate at LHC. Here's the total rate for Higgsino pair production. It's at the 10 to 2 to the 10 to the 4 femtobarn level, which means in the current run 2 data sample, you'd have about 10 to the 4, 10 to the 6 events. Normally, these things are quasi-visible because the heavier Higgsinos decay to lighter Higgsinos with a very small mass gap, and so there's very small visible energy release, and they would be invisible if you've got R parity violating decays. Then these things should stand out like a sore thumb. The lambda couplings give you 4 lepton plus missing energy events. The lambda double prime give you 3 plus 3 jet events, where the 3 jets resonantly reconstruct the LSP mass. And so far, LHC hasn't seen anything like these types of events, although their limits don't exactly apply to this model. And so you can hide the LSP decays if the LSP decays after leaving the detector, and that's the case when you live at the 10 to the minus 7 suppression, then you still get hidden Higgsinos at the LHC, and all Axion dark matter, so it's hiding from wind detection experiments. So I'll end there with these conclusions that basically the under rather general scenarios that are solved by the discrete R symmetries, we expect Q1, PQ, and R parity conservation both to emerge as accidental approximate symmetries. We can solve the strong CP problem, but in some cases where we got suppression of terms by FA over M Planck, then we glimpse all the K array in the Rho universe, leaving only axions, and the axion coupling was highly suppressed in this sort of a model. So we would expect LHC to ultimately, hopefully, generate Higgsino pair signals or other SUSY signals in the coming years. But we probably won't see dark matter.
Any questions? 2 questions, Howie. First, you were showing one plot with the A terms, and they were all 10 TeV or higher, if I remember correctly.
Yeah.
What is the value of the diagonal entries of the, in this case, stop mass matrix?
Well, we usually, I'm trying to go backwards here. We're usually trying to generate these models in the landscape. And in the landscape, the different soft terms have different functional dependencies, and so they effectively act as independent terms in the multiverse. So the first 2 generations actually get pulled up to large masses around 30 to 40 TeV, and they get pulled up to a common upper bound due to Steve Martin's 2-loop RGEs. They're flavor independent, and that landscape offers its own solution to the flavor problem. Since the 3rd generation has a big Yukawa coupling, it only gets pulled up to 5 to 10 TeV on the soft terms, and then you feed those into the top spark mass matrix. Along with large mixing, because the A parameter gets pulled up big too, that jacks up the Higgs mass and reduces the fine tuning contribution. So you get top sparks around 1 to 2.5 TeV. So those are the types of benchmark models we use. But for these things, we put in 10 TeV for the X and Y soft masses. And this A parameter was about minus 3 times that value in order.
But the A term on the next slide is also the A top?
No, that's not.
Okay.
That's the A term in this non-renormalizable operator. So it's Planck suppressed. Here's a soft term. This is a Planck suppressed term that corresponds to these quartic terms and superpotential from the base model. So you have these quartic terms that are actually suppressed by an atomic, and that's the A term corresponding to that.
Any other questions? If not, I sent Hardy again, so I'll clear.
We got it.
Oh, so actually, I have a secret thing that I think can be, that's what you need for DWS. Is you need actually you need to find the inverse horizon
Yeah, I don't go very deep.
And in open systems.
Yeah.
That's not necessary.
That's all right. I developed a little adequate. Yeah, I don't know. Otherwise, it's one way, but you don't want.
Yeah, they're not.
But I don't know. That's something I show them for, but it's not exactly right. That's the advantage. That's why you have to second one case.
Okay. Maybe it's Japan.
There.
Yeah, I like unboxed with folder with awesome. Yes.
So, I think we should start the last session before we got over the first Jordan.
Yes. Hello, everybody. First, thank you to the organizer. It's my first time here for this workshop, not Minneapolis, but for this workshop. I appreciate it a lot. But this also may also explain that his talk is slightly different than the others. The workshop is very interesting, but it's also very theoretical. I can acknowledge this. And so this will be probably the most down-to-earth talk of the whole workshop. I will talk about LHC and experimental limits sometimes. And so don't get frightened by this. It's a real connection to the real world, for sure. I always like to put a cartoon. You can look it up also later. I put the PDF on the Steam doc. I also have a Trump joke here, but you can look it up later. Right?
Oh, you might get extradited to El Salvador.
I hope. Well, my flight was canceled. The other thing, my flight was canceled, and after this I have to rush out to fix this. So Karim, I'm sorry, but I want to fix this before dinner. Therefore, after my talk, I have to leave to talk to Air Canada to arrange something. Now, the title that I put, no light. Jen? This okay, sorry. So, yes, the original title was BS and Higgs sectors of future experiments. But this is a far too vast area to cover it here. And therefore, first of all, I changed the first line to BS and Higgs reduction. So it's a well-defined subtopic. And I can tell you, if you're not so familiar with current analysis at the LHC or Higgs searches, etc., this is really one of the topics that is most people are working on at the LHC. Yeah? It's really a topic that Atlas themselves are putting a lot of resources in, and we will see in a moment why this is the case. But this is still a bit broad, and so I do BSM, the Higgs reduction at the high luminosity LHC and at future plus-minus colliders. I have some introduction to motivate what I do. I will tell you a little bit about resonant Higgs production. That's the first part, resonant Higgs production at the LHC, and I show you why the results of the LHC do not help us right now. They're not really reliable. And then, if time runs out, I want to talk about our future. You know that in Europe there is this European strategy update ongoing, and the next machine should be in a plus-minus collider. The question is linear or circular. Yeah, I think this is the main question that people are struggling about. And there are many things said about triple Higgs couplings, how they can be measured. And I want to give you a small update on this and show you some new developments in this. Good. So let's get started. Introduction. This was said a few times already. Gravitational waves also play a role here, or can play a role here. And I find it fascinating that there is a connection between Higgs physics and gravitational wave physics. And just to spell it out once more, the big question we are after is, why is there more matter than antimatter? Possible solution, electric baryogenesis. This, on the other hand, requires a first-order electric phase transition in the early universe, which is not possible in the standard model, and requires BSM Higgs sector. So this is the main motivation for me, that we really should look for a BSM Higgs sector, additional Higgs boson. Bonus, we might be able to see gravitational waves detectable with LISA. We discussed similar things during yesterday and today, but this could happen here as well. So I can be a bit shorter in this part of the motivation. Just one more thing. This is the thermal evolution as we would expect it in the standard model of the Higgs potential. This is higher temperature, then we go to lower temperature. This is the minimum, and this is then a smooth roll over to the minimum here to the left where we are right now. No first order electric phase transition, doesn't help us with electric baryogenesis. We need a Higgs sector that gives us the left-hand side, where we have a barrier here forming. And at some point at the temperature Tc, they're at the same level, and at Tn we tunnel through. This is the disruptive moment where we have the first order electric phase transition that helps us with electric baryogenesis. This is what we are after. And we have to check which model can provide us with some. I can skip the one how gravitational waves are created. Just one photo. We talked about LISA. We haven't seen LISA. This is LISA. These three satellites and the second Lagrange point, and each arm here is, I think, 2.5 million kilometers. So it's a quite big experiment. The good thing is it's the only one that is approved from all these space-based experiments, and the launch date is something like 2035. Good. Now, back to the BSM Higgs sectors. Usually you see a picture where one says, we only know the minimum, and then we have to see how it evolves at lower values of the field and higher values of the field. This is a far too simple picture. This is a much more realistic picture, although it's drawn by hand. This is what we know right now. The electric vacuum here, the Higgs mass gives us the curvature. But then with additional Higgs bosons, we can have other minima, deeper minima. We have an absolute minimum. Several particles are possible to get there, etc. So the structure of the Higgs potential can be much, much more complicated. Yeah, and very little is known. Yeah, so we know only a little bit around here. We don't know anything about all of this. But since we want the BSM Higgs sector with additional states, something like this is likely realized in motion. And now we come to the connection to the measurements. It is clear that the trilinear Higgs couplings are responsible or play a big role in the form of the Higgs potential. And therefore, a huge amount of working time is devoted at the LHC to extract or to measure trilinear Higgs coupling. First of all, to measure the Higgs production. Yeah, if you have the Higgs production here, blue, top triangle Higgs, and then you have the Higgs. This is what they're looking for. And here the triple Higgs coupling enters, the one that we also have in the standard model. However, if we have BSM Higgs physics, we can also have this kind of diagram here. We have a heavy Higgs boson that can be resonant and can give us additional features that I will show you in a moment. Importantly, also, we have this kind of box diagram here, which doesn't have triple Higgs coupling, but the interference is very important. What I want to stress here, we not only should look out to measure this trilinear Higgs coupling, that is present in the standard model. If we want to reconstruct the Higgs potential and know how the thermal history really works, we have to measure all the triple Higgs couplings. It's not clear how many of them will be accessible, but at least one of them might be accessible. It's exactly this one. One heavy, two light. So we should measure all of them. Often I use the abbreviation kappa lambda, which is the ratio of the triple Higgs coupling divided by the standard model value, and then we good. As I said, we need BSM Higgs physics. And there are two models that I will use in this talk as examples. You can call them toy models, but they are real realization of BSM Higgs sectors and extension. This is the most simple extension, and therefore it's very well suited to study certain effects without getting distracted by other stuff around. We have the doublet that we have in the standard model, and then we just add just the one singlet here, the S with its vacuum expectation value, the Higgs potential with all the terms that are allowed. The two mass eigenstates are related. There's a mixing angle to diagonalize mass matrix, everything very simple. This is really the simple Higgs sector extension that teaches us a strong first order electric phase transition. So therefore, it's very well suited for analysis. The other model is the 2x doublet model. I spare the details, two doublets. We have 5 physical Higgs bosons here. This is the one that we are after in the end. And we have 2 mixing angles, alpha and beta, encoded in this cosine beta minus alpha 10 to beta, and then all these other parameters to give us the description of the model. And here it's obvious that there are many, many more triple Higgs couples. And in principle, we should aim to measure all of them. I don't know how, but we should look for possibilities to measure all of them at the future colliders. I have to mention supersymmetry. I wear my MSSM t-shirt here. It's very well known that there are 4 types of the 2HDM coming from the Z2 symmetry that is introduced to avoid the flavor changing neutral currents. And then the famous type 2 is the one that we find in symmetry. And most of the examples I show will be either type 1, where all the fermions couple to the same doublet, or type 2, which is exactly the SUSY type. Good. Now, getting back to the Higgs production, and now in the first real part, the results resonant the Higgs production. Let's look first at these two diagrams, which are present in the standard model. There is a destructive interference between these two diagrams. And this is the reason why the cross-section is so small. And here is the calculation of the cross-section as a function of this kappa lambda, or the triple Higgs coupling, divided by the standard model value. So you take the standard model and simply vary the trilinear Higgs coupling. Don't get me into it whether this is consistent or not. This is what's done in order to see the dependence. And one sees here, 1 is the standard model, this here is the curve, and one sees this negative interference. We make lambda larger, interference, the destructiveness becomes stronger, the cross-section goes down, has a minimum around 2.5, and then starts to grow again. This is all well known. One important thing here is, I have more of this in the backup. We include higher order corrections to the trilinear Higgs couplings, at least the 1-loop corrections. They are known in some models up to 2-loop. And these corrections can be huge. They are of electroweak size, but it's this kind of diagrams that enter, where we have here a heavy Higgs boson. And these couplings, light Higgs and 2 heavy ones, are not present at the tree level. They can be quite large, and they can give contributions and can enhance these trilinear Higgs coupling by a factor of 10 or something like this. You may ask about the perturbativity. If you calculate 2-loop, you will find that 2-loop is substantially smaller than 1-loop, so perturbativity is not an issue. And one can also ask, is it consistent to take this into account and not this, for example, is much harder to calculate, yeah, a double box. It is consistent, first of all, in terms of power counting. This is a small subset, a closed subset. And if this coupling here is much larger than the Yukawa coupling here, it's also the dominant part of the corrections. So this is okay. One more slide as a real example. When I say we have this first order electric phase transition in our BSM models, I have here one example from the 2x doublet model. We did a parameter scan to see where we find the first order phase transition. And I will not go into the very various details. This is the parameter space, the mass difference between the heaviest to the odd and the heaviest to the even one. Here we have again our beloved kappa lambda. We find several thermal histories. The important one is this what's labeled E. E is the one where we have the strong first order phase transition. This is the part of parameter space that is logically favored because we get, or we might get, something like electric diagonalities. And one can see that in this area here, this kappa lambda is between 1.5 and 2. So it's substantially lifted away from the standard model value. If you also want, as the bonus, the gravitational waves, this is here this pinkish area, then the kappa lambda is around 2. But this is not a requirement. What would be just nice to have. Now, let's come to what's done at the LHC. There, they look for resonant and non-resonant Higgs production. I said here I want to focus on resonant Higgs production. And in the DSM models, as I said before, we of course have not only these two standard model type diagrams, we also have this diagram, and we have the interference of this diagram with the rest of the contributing diagrams. The experimental limits are obtained, as I said, in two limits, in two ways. Either our experimental friends assume only these two diagrams contribute non-resonant production, they ignore this one, or they say, oh, we have a heavy Higgs. We forget about these two, we take only this one into account. And I will show you that because of this simplification they're making, the limits that are obtained nowadays are unfortunately not applicable to realistic models. I show you one example in the 2HDM. We have examples in other models in this Higgs singlet extension as well. Good. Now, how is this done from the experimental side? They not only look at the total cross-section, they look at the differential cross-section with respect to the invariant mass of the di-Higgs. Yeah, this MHH, this invariant mass of the di-Higgs pair, starts of course at 250, 2 times 125. Standard model is this black line, goes up, goes down. This is what we expect. Now, if we have a heavy Higgs in the game, we see a kind of, let's look at the red line, where everything is at, trillion Higgs couplings at tree level, goes up, then we have a dip, we have a peak with exactly this resonance structure that we expect, and then it goes down. Taking higher order corrections into account, it's completely deformed, and what we find is this line here starts not at low values, starts at very high values, has then a kind of plateau here, has then the peak where the mass is sitting, and then falls off. This is what you can calculate in the 2HDM. This is one example point. And I was talking about large higher order corrections. You can see here, tree level, kappa lambda is 1, standard model value, one loop level, 3.6. Yeah, and this brings you also into the interesting area. Good. One more thing.
Sorry, so one loop will become back to a bump again. So at tree level, it's a bump and deep structure.
Yeah.
But at one loop level, the full result is a pure bump.
It's a kind of a pure peak. Here's a blue peak. The bump, we have this destructive interference here between the resonant and the non-resonant diagrams that gives us this kind of plateau. Well, it comes effectively from a large value of kappa lambda. Yeah, this causes this change in the shape. And this kind of gets rid of the dip, and we are only left with the peak. But this is one example. We find all the peak structures at one loop or so. Yeah, there are more things to consider because, first of all, the detector are not perfect, and you don't not always measure the correct MHH value. You have a smearing around this, and then you also don't get the result as finely binned. You have here bins in this MHH at the order of 50 GeV. Red line, realistic calculation. In the end, you get this shape out. Yeah, this doesn't look as nice anymore. What our experimental friends are doing for the resonant Higgs production, they calculate the blue line and then they end up with this one. Now, I show you one example for sake of time that we evaluated. It's a point that is allowed by all current theoretical and experimental constraints. So, a completely viable point. And according to the Atlas analysis, which is stronger here, the point is excluded from resonant Higgs production. Yeah, we have the mass of 450 GeV for the heavy Higgs. The other Higgs masses do not play a big role. You see the parameters here. Kappa lambda is 5 at the one loop level. However, the Atlas exclusion is based on distributions that look like this. A very clear peak, very easy to find. The realistic picture is this one here, the red one, where we have a little shoulder and then this falls off. We asked our experimental friends, is this applicable? And the result is nobody knows. Yeah, it's just not known. And this shows us that the experimental analysis have to be redone in order to make them applicable to models that are viable and technologically interesting as we've selected. Good, we have another example that I skipped. How much time do I have left?
7 minutes.
7 minutes. Then I also skip what we can learn if we look at the MHH distributions in more detail. there's a lot to be learned if you do it right. And we believe that we can have access to these BSM trilinear Higgs coupling. But yeah, let me just summarize this here. Large parameter spaces with relatively low heavy Higgs masses are still allowed. BSM Higgs sectors predict this kappa lambda different from 1. Set the first order electric phase transition favors values of 1.5 to 2. BSM Higgs sectors give us additional trilinear Higgs couplings. You get access to these at the Heinemeyer LHC or also at the LHC right now. Try to find it via this process blue to Higgs. And here these MHH distributions are crucial. For low values of MHH, kappa lambda is the driving factor. When this MHH is around the heavy Higgs mass, we get this peak dip or the peak structure caused by this trilinear Higgs coupling. And we did an analysis in this singlet extension that I just skipped, but it indicates that there may be experimental sensitivity to this BSM trilinear Higgs coupling. Nobody from the experimental side has this done so far, but we try to emphasize to them that this must be done from not only from the theoretical side, but also with a realistic experimental analysis. But in the last 5 minutes that I have, let me talk about this crucial decision that we have to take in the very near future, circular or linear. Yeah, this cartoon sums the situation up pretty well. This is a famous plot that shows from the last European strategy update, the precision that you can get from the various colliders of the trilinear Higgs coupling. This kappa 3 is the kappa lambda, again here. Heinemeyer LHC was set so far 50%. It has become a little bit better with the last, a few weeks ago, there was an update, but this was for many years level. You could measure kappa 3 at the level of 50% at the one loop level, at the 1 sigma level, meaning at the 2 sigma level, you can say whether it's 0 or not. Not so good. If you have circular machines, then you can make analysis. I'll show this to you in a moment. Only by an EFT analysis where the trilinear Higgs coupling enters at the 1 loop level, and then you can try to extract values of it indirectly. Whereas at linear machines, you can go to higher energies, and therefore you can produce 2 Higgses and have direct access to the trilinear Higgs coupling. Now, this is the big difference between circular and linear. And one can see here the 2 linear machines, IOC and click, depending on the energies. These are also old analysis. I'll show you some updates in a moment. They could get access between 25 and 10% here, or here also up to 10% at click. At CCEE, what CERN or many people at CERN want as the next flagship project, they, I'll show this to you, they measure at several energies, and then depending on the luminosity or so, they start at 50% and then claim to go down to 25%. We'll come back to this in a moment. As I said, there are many open questions that are completely neglected in this kind of analysis. It's not all these precisions are obtained assuming kappa lambda equal to 1. I try to convince you that this is not a very good assumption. And also, the presence of BSM Higgses has completely been neglected in this kind of analysis. Again, not a very good assumption. Now, I skipped the updates that have been produced recently and show you this plot here. This is an analysis that has been done for the FCC, a SWEFT analysis, where they take measurements at 240 GeV and 365 GeV. This is the highest energy where they claim to be able to get. And then these are the modifiers of the coupling, this delta kappa lambda for the trilinear Higgs coupling and the HZZ coupling. It's probably a delta of CZ. You get this band here for 240 GeV, and then this ellipse here to 65, and then this overlap area between the two, which gives precision of this kappa lambda at the level of 30%. Doesn't sound too bad. Yeah, you can see here example diagrams. For example, here E plus minus to that H, and here by the scoop correction. And here is the point where the trilinear Higgs coupling enters, where they try to extract this coupling. Yeah, and these are other diagrams. And now, this precision or this analysis was done 1 loop level and inserting kappa lambda or the effective operator for that exactly here as I showed it to you. Here, here, here. However, all other possible contributions at this level have been neglected. So you insert in your calculation exactly 1 parameter you want to measure. You set all other parameters to 0. And then we get to 30%. I find this questionable, and luckily there was a group about half a year ago, Giardino and Dawson, for example, from Brookhaven Lab, and they did a calculation where they took into account all the diagrams at the same level. They didn't do a fit to these functions, but they showed that the effects can be substantial. And I take this here from another talk that I stole this. This is the diagram that has been taken into account so far, and other diagrams have been neglected. There's a famous one, E plus and minus, and here with the top loop or so. It's exactly the same loop level. And for example, this kind of effective operators is quite unknown, and therefore the analysis is currently being redone. I have no idea how the results look like. I have to finish. There have been more analysis at the IRC, and they indicate that the precision is substantially better than the old ones from 2019. I show you one example. This is again these delta, this kappa lambda, this is the standard model value, and one can see that now with the new analysis at the IRC, what they call 550, they go 50 GD up, that for the standard model value, instead of 28%, you get now plus minus 15%. If you go to the experimentally possibly favored value of 2, you get a plus minus 9% determination. Okay. These are the latest numbers here. And we hope that this kind of consideration will have some impact on the decision on the future of the next generation project. I skipped this one here. And these are my conclusions, but I think I said everything. We have very likely kappa lambda not equal to 1. We have very likely BSM triple Higgs couplings. We should try to measure all of them. There's no experimental analysis for BSM triple Higgs couplings, but we believe that they're accessible at the High-Lumi LHC and for sure also at future plus minus colliders if the heavy Higgs is in the kinematic reach. The resonant Higgs productions give non-reliable results, unfortunately. We try to work with our experimental friends to improve this. Kappa lambda measurements at circuit colliders have to be redone as well. It's a work in progress. We don't know the results yet, but the relevant degradation is expected. And at the linear colliders, these results look substantially better than previously. Thanks a lot.
Yes. Yeah. What's your personal opinion about the European strategy?
This is a trap.
It's too much dominated by some people at CERN that try to push through their pet project. And I don't think it's done in a very healthy way. Yeah.
Doesn't tell me much.
Okay. At CERN, the proposed project is the FCC. And FCC is FCCE plus FCCHH. And from the last strategy, it was said we should do a feasibility study that should show the technological and financial feasibility. They had a lot of time. Technologically, at least the FCCE is possible. FCCHH, nobody knows how to build the magnets and how much they will cost. The price tag, they put a price tag now on FCCE and FCCHH. And depending what you do, FCCE is around 15 billion. And then you add another, I think, 18 billion for FCCHH, where you don't really know how much the magnets are. But this goes far beyond the CERN budget. They have no idea how to finance it. And they still want to say that this is what we want. We will see how this ends. Yeah? There is a new proposal, a linear collider facility at CERN. There's also some input for the European strategy update, where also some plots that I've shown to you are from. And they have shown that this could actually be constructed within the CERN budget, which might be a bonus, yeah? Because what is the best future collider? The best future collider is the one that we get, that we can build, yeah? We can dream of what we want to have and what would be nice or so, yeah. If we can't afford it, we don't get anything. We can get one, we should go for it. I hope this answered some of your questions. If not, we have a bit of tonight.
Are you saying for that linear is click?
Click would be nice, but the linear client facility at CERN is a kind of IOC machine. But once you have the tunnel, you can also reuse it then for a different machine later on if you want. There are also other ideas, half plasma, half, let's say, normal electron collider or so, yeah. People are talking about alternatives.
So I have a comment and a question.
Yeah.
My comment is regarding your second to last point about re-evaluation needed for kappa lambda and circular collider. We actually did that around 2018 with the DESI group, turn on all the operators and many loop effect taken into account. The result degraded to 50%.
Can you give me this? I'm not aware of anything this time.
So we did that, and I think recently in the European strategy update, the FCCE group, they further refined our analysis, and the results still degraded.
This might go to too many details, yeah. I don't think what Giardino and Dawson did recently had been done before. If you tell me it had been done before, I'm surprised.
I can show you.
We discuss it over here.
The question is, you see the NL effect is large and changes all your line shapes. Right?
Yes.
I also did a lot of interference study, but personally, I find it's really hard to let experimentalists do those analyses because it's too much variations depending on your parameters. So, what's your resolution on that? Are you?
The experimentalist will have to do analysis in a higher dimensional parameter space. They have to assume a first resonance with the mass as a free parameter, width as a free parameter, Fallon Higgs coupling times Tsukava coupling, Tokugawa coupling as a free parameter, and then they have to redo the analysis in this higher dimensional parameter space, and then it can be used for other models. Otherwise, I don't see a way to.
I agree, but that's a lot of additional work. Now,
yes,
if you are convinced to do this.
Yes. A less political question. You said things like it's very likely that kappa lambda is not one, etc. I mean, this is not based on data, really, right? This is based on your first line of this slide. So there's leptogenesis as an alternative where you don't need to mess with the Higgs sector, really. And
if you don't want electric baryogenesis, if you don't want a strong first electric phase transition, then you can do it in the standard model if you want. Yeah. But
so, I mean, is there any experimental evidence that kappa lambda should be bigger than one? I don't think so, right?
The current limit, well, they don't have a measurement, obviously, yeah? There are only upper limits on the cross-section measurement, this mu value, yeah, the cross-section times branching ratio. Divided by the standard model expectation is, I think, 2.4 plus minus 1 point something or so. Yeah, so far we are not there. But I believe with 1.3 we will know a lot more already. And at least for the cross section as such, we will get an idea. I think so. But yeah, so far not, unfortunately.
Okay. I guess for the linear collider would be important really to also realize the high energy options, right?
Well, 550 is already quite good, as I showed you. Okay, let me just, I know we are pressed in time, but yeah. This is the 550 option, is the green one. You can see the green bars here. I think it looks quite good. Okay, I stop.
I see you should stop now. Thanks again.
Sven, you laptop.
That's a very good idea.
There it is.
This gets too excited that this one was
No, you just undid something.
It's not stable.
Good way. Yeah, I was like,
Thanks.
Okay. Sorry for the delays. I would like to talk about some basic field theory. It's not even content, it's classical field theory, the basic problem that's there for now nearly a century. It's not been totally solved, and present what we have done as progress on this. This work is based with work with collaborators when she's here in the auditorium. This Bruno Clock is HPTR field permanent. These are students in Brazil. There's not under policy. The first thing I would like to start with is what I mean by high spins. Because in the literature nowadays, people, when they speak about high spins, they are massless fields. For me, they have to be massive. Also, in the literature, often now people say higher spin or spin bigger than 2. For me, is spin bigger than 1, which here we will really discuss spin 3 hard and spin 2. And the new thing is that I want them to be charged, have electrical charge, and I would like to consider them propagating in a constant electromagnetic background. But before we go into the case which we charge and electromagnetic background, let me just remind you some basic facts. The spin 3 half first. The spin 3 half usually is presented as psi mu. Psi is a spinor, mu vector index. This makes 2 times 4, 8 degrees of freedom for following u, psi 2. And so 8, why you know that this particle has to have 4 degrees of freedom, so you have to get rid of 4. And this you get rid of them from imposing this condition. Remember, psi has alpha dot indices, so we have here there are 2 equations. Here there are 2 equations, and so you remain from 8 minus 4 is 4 degrees. And this is the field Pauli system, and you can get this the Quark equation and the constraint from Lagrangian that was derived by Einstein Schwinger a few years after that Fields and Pauli wrote this system. Now, if you go to the spin 2, this one is probably also very well known by most of you. You get symmetric tensor H and N. This has 10 degrees of freedom, and you know that you should have only 5 degrees of freedom, which correspond to the spin projection minus 2 plus 2. And so you need to get rid of 5, and you get rid of 4 here with n as more values and 1 on the trace, and so you remain with 5 degrees of freedom. This is the first Pauli for the massive spin. And it's very well known, things by maybe all of you, but this system, you can get it from Lagrange. It's called the first Pauli Lagrangian, which has as kinetic terms the quadratic expansion of the Einstein reflection, so it's like a gravity star. But for which are this mass term with this special combination. So this is what you do with the neutral case. Now let me go into what I would like to describe to you. And this problem when you fit in when you put charge for this state, the spin 3.5 and spin 2. So let's go back to the history. Dirac in 1936, he writes this royal proceeding, which is titled relativity wave equation. And it says So I just produced here the I reproduce here what is written here. So he says that the elementary particles now to present day, so in 1936, are the electron, positron, neutron, and proton, all have a spin 1/2. And that's the work of the present paper. We have no immediate physical application. But he says that all the same, it is that we have equation ready for a possible future discovery of an elementary particle with a spin greater than 1/2, or for an approximate application to composite particles that should have any kind of spin bigger than that. And then he finishes by saying that further, the underlying theory is considered mathematical interest. So where do we stand? Later, we have discovered some composite particle, which is this one is famous, omega minus, which has large, massive. And I choose this one because it was discovered propagating in a constant magnetic field. It's here. And so it's in a lower chamber. And this also seen in the 1964, and it has led to the theory of Quark. So what Dirac wanted is here since 1960. Now, we have this charged particle of different spins, and we want them to propagate in electromagnetic background. So Dirac says, okay, what we would say for any of your student, undergraduate, graduate, whatever, what you do is you take the partial derivative and the covariant derivative. This is what we claimed. Unfortunately, this is the problem. So if you do that, it doesn't work. In fact, you get theory which either have some problem with quantization. The quantization becomes non-causal, or you have a subliminal propagation, which means they are causal, there is no causality, or you get that some of the integral degrees of freedom start to propagate, so the theory is pathological. And what I will do next is to explain to you, to give you example how this thing happened and what people did to try to solve this problem. So let's start with the massive spin 2. I wrote the equation before, the equation about the fierce Pauli with the partial derivative, and you can decide to do as Dirac proposed, just replacing with covariant derivative. The problem is that when you do that, you take this equation of motion and you commute it with a covariant derivative, and you will get a new constraint. So you get too many constraints. So you get less than 5 degrees of freedom. And the theory is pathological. And that was what Fierce did just after 1936, and they discovered that you cannot go this way. So what to do? So after that, Fierce wrote what I just presented and found that this is not the right way to deal with spin 2 massive charge in electromagnetic background. They worked with Fierce and Pauli, and they wrote a paper which says that they call it on relativistic wave equation of particle about the spin in an electromagnetic field, and they say it's very easy to do without charge if you don't have an electromagnetic background. And so they wrote what is known and what are represented as the Fierce Pauli Lagrangian, and the equation people well know. But the difficult problem is when you put the electromagnetic field. So this problem remains up to today. Progress was made by Federbush in 1960, And he proposed that you take the minimal coupling and you add some term, which is this dipole coupling to the spin 2. Yeah, this spin 2 field. So in my notation of H, you add this term. And so here, the coefficient is the geomagnetic ratio. And if you add this term, then you try to get the equation of motion in this constraint. And you find the constraint, which was that the trace of H is 0, now takes this form. So you understand that if G was equal to 0, then you get that the trace has an equation of motion and will propagate. While H, we wanted the trace H to be 0. So it was a constraint. So you see that G cannot be 0. That was the problem that we had before. And to cancel this term, he says, okay, so now you have to put G for 1. And this way, the problem seems to have been solved. However, the problem, in fact, there was another problem that he was not aware of, and Fields and Pauli were not aware of, was that this theory has some superluminal propagation. And so if you look at the characteristic active surfaces of this theory, you find that what should be the light cone equal to 1. It's not, it's superluminal. It's you see that N0 is N is the vector to the surface propagation of the wave, the front wave, and this is bigger than 1. So you propagate outside of the light cone and you are non-causal. So causality is violated, and this happens with any value of the field, as small as you want. So it's really a problem, and people wanted to solve it. So the solution of this was try to look in string theory. String theory had, if you look at open string, a string is just represented here, vibrates, and the different modes of vibration give you different particles. And there is the light state, but they have the heavy oscillators, the heavy mode of string theory, which are the whole the string scale. And those, you have all kinds of spins. They are massive, and they are what are called rigid trajectories. And among them, you have the spin 2, and you can put the string in an electromagnetic background. And from the low energy point of view, the string oscillation, the string mode, looks like if it is composite spin 2 particle, which is charged and propagating in a magnetic electromagnetic background. So Argyres and Napkin Princeton did this exercise and derived the Lagrangian and the equation of motion for the heavy mode, which corresponds to spin 2, which is spin 2 massive charge propagating. And they found so the difference with the Federer-Busch Lagrangian. If you see that instead of coefficient 1 here, which was what I told you you need so that you don't have propagation of the trace, we have a coefficient which is 4, which is what corresponds to a geomagnetic ratio, which is equal to 2, which would like to have for unitarity. Okay, so they wrote Lagrangian, they wrote the equation of motion that I will present later. So they have something which which works for the problem of causality. It's a causal theory, But the Lagrangian has not just this term, as I told you. If you have just this term, then you get the Bush Lagrangian with a wrong coefficient, so that you will have H which is propagating. But you have an infinite series of terms with expansion in F, which are there to cancel the second term of the equation for the tracer. So this Lagrangian unfortunately is constant only in equal 26. So only in 26 dimension you have the Lagrangian, which answers the question how you write Lagrangian for spin massive in electromagnetic background. This is the form of the Lagrangian. What happens is, compared to what people tried to do before, is that you, instead of this field H, you have to introduce some dressing of your spin-proof field with electromagnetic background. This is the Q times F nu, and then this appears in the kinetic tab. If you want to go to canonical kinetic tab, then you have to make an expansion in F nu, which gives you all the infinite series I talked before. And you see the equation of motion are written here. And I rewrite them here. So if you look at their form, you see that if you have guessed them, without going into this computation with a string field theory, you could have guessed them because if you look at Proctor equation, this is just a generalization of Proctor, the way you write it for spin one. So this is quite easy. But then people try to guess for spin 3/2, and you cannot guess it. It's really complicated, and this is what we have done with Wenqi and my collaborators, and I will present how they look like. So the chart we have case. Somebody who tried to guess the Lagrangian equation of motion was Simon Desert. He wrote many papers. This is one of his papers, and he says that whatever the formal problems is not as effective time, the spin theory must be constructed since approximately localized higher spin particle exists, omega minus 1. So you should find the equation of motion of Lagrangian. It should have to exist. You have to be able to write. But he tried everything, and he didn't succeed. And he says our study of causality showed that no model maintaining the correct degrees of freedom avoid sharing the pathology of the minimal one. So he didn't succeed. So what we did, so with Nathan Berkowitz and his student, we decided to do like RGS and NAPI and do a string field theory and try to find the solution from string field theory. But the problem is much harder than the one of RGS and NAPI, because when you go to the supersymmetric case to get a spin 3/2, the computation becomes much harder, and you have much more fields. Instead of there was only one field in which was the spin 2 in the case of bosonic strings. You have 12 fermions and 12 bosons. And after 2 years of computation with the students, we got to this awful space Lagrangian. The student didn't want to continue, so when she volunteered to expand it, you had something like 20 fields between auxiliary fields and some Gauss and anti-Gauss, but sphericity formalists. You had to get rid of them, and we got the result. But before going to the result, I will show you way after that we understood it. So let's go back to the neutral case. You write the graph equation and the two constraints. one is the trace constraint and the other one divergence constraint. And in fact, just by one constraint is enough. You take this trace constraint and put it in the equation of motion, say that it should be always valid along the propagation, you get the second one. And when people, because I have 5 minutes, when people try to build equation of motion and Lagrangian for this spin half charge, what happens is usually instead of gamma mu psi mu equal to 0, they get some matrix which contracts psi mu and gamma matrix, and this matrix are always determined, which vanishes at some value of the electromagnetic field, and then this constraint disappears in that case, and so you have one less constraint. So you lose this constraint. So you understand that you have some fields that should not be there that propagate. So the thing is that you can say, okay, let me impose that this constraint remains everywhere. And Farati and Rahman proposed that in 2009. And they tried to find an answer for Lagrangian equation of motion. And what they found is some infinite expansion in F square, dimensionless quantities, and or F of T. And this is an infinite, and at every order, you get non-causal, and you have to use the other order to cancel this causality. Because the causality appears always with a small term, which is the order. So that was not useful. It's interesting because that shows that there is a solution, but it's not useful because the equation of motion with infinite terms that we are always trying to deal is not what we want. So with Wanty and Wimmer-Lefloc, after we have found the equation, we decided to go back to, because we found this, to go back to this and see if we can find it just by requiring that this condition is valid all the time. So, and we were able to manage. And in fact, this was enough to found the form of the equation. So this is what generalizes the Dirac equation of spin 3 in the case of presence of electromagnetic field. Epsilon Mn is the electromagnetic field. So this Dirac equation was 0. Then there is the second term, and there is projection, the chiral projection psi left or psi right, have to choose. You will never have thought about putting something like this in the second term. And also there is this modification of the divergence constraint, which it looks very weird. No one would have thought putting this kind of form. So it was not possible to guess it like it would have been possible for the spin 2 case. But this is the form that you get, which is causal, which gives you geomagnetic ratio, which is equal to 2, which has everything you want, and you can generalize it. You can generalize the equation for any spin, that, which we wrote with Wimmer-Lefloc and Wanty. Any spin which is integer or half integer. This is easy to understand. This was more complicated. Conclusion. So I rewrite what Dirac wanted. So Dirac wanted the equation. We found the equation. But then Fierce and Pauli, when they came, they said, oh, the equation of motion is difficult to guess the constant. We go with them. So let's have a trick. Instead of writing equation of motion and trying to guess the constraint, let's try to find the Lagrangian, which gives you the equation of motion and the constraint. And for 8 years, that program didn't succeed. So we have been able to find the equation of motion. So we solved the problem of Dirac, but the problem of finding the Lagrangian as Fierce and Pauli wanted is still happening. Okay, thank you.
Questions?
Yes, Roman. I guess two questions. One, if you do like Kaluza-Klein reduction on a cylinder, then of course there's the sort of charge that comes from the graviphoton that comes there. And then the KK gravitons would have spin 2 and charge. Does that give you any, it's like your string theory example or something that, because you have a UV understanding of what's going on, is that a simpler place to sort of try and match onto a, of course it is a Lagrangian, but it contains a whole tower of charged gravitons.
Yes, and the thing is that if you look at the Kaluza-Klein compared to the massive oscillators, they have a geometric G for 2, and then this is needed for unitarity, and that makes them that if you are able to separate one of them from the rest of the tower, then you get a term which is consistent. The Kaluza-Klein now they have G for 1. And you cannot separate. When you try to write a theory, just try to separate one of them, then you find that it has pathologies. So this is
But so then the question is, if you had this Lagrangian, I'm trying to just see the regime in which you could hope to apply it. I would have thought you would only use it for the charged particle barreling along and softly interacting with soft photons, rather than anything very hard, because as far as I understand, like for higher spin 2, for spin 2, massive spin 2, the theory doesn't make sense. There is no theory. We don't expect there to be a sensible dynamics for an isolated spin 2 with hard interactions, with energy transfers, momentum transfers of order the mass. So is this an effective theory for, it's like a heavy particle effective Lagrangian that you're looking for?
Yeah, this the answer is quite long, but let me try to tell you. There are it's not first. There are many questions that are raised when trying to address this question that we don't know the answer. The fact that you cannot get the spin 2 or spin 3.5 massive just by itself, no one proved it when it's massive. When it's massless, you know, if there are theorems, and when it's massive, there are some kind of laws, and then if you look at one of the questions which was raised by we did it is try to understand the massive mode of string theory, and then can you isolate like one of the modes, which in which case it looks at this level that you could isolate the spin 2 in the bosonic string, but you can isolate it with keeping the lightest modes, but we know bosonic string has Axion, so it's problematic. While if you take other spins in the bosonic string, it looks that you cannot just isolate them. And for the supersymmetric case, we don't know the answer. So this Lagrangian, this comes with non-canonical term, as I showed, which normally if you try to write something like that, gives you ghosts. And in string theory, it happens that contrary to what one would expect, there are no ghosts, and you can prove it. There is a proof for the 3 case in Wojcicki book, you can continue to use it. So what happened? So these are all kind of, let's say, formal questions. And then if you want the application, then of course, you have composite particle. You don't want to have a big energy for your photons, otherwise you start have form factors that appear. And so yeah, then what we tried already, equation of motion, there is omega minus. It propagates for something like 5 centimeters, so you can consider it like one particle. Try to find an equation of motion, but all right. And then it's an effective filter is say. There are many questions which are raised there. Don't have no answer your question.
Yeah, in part it is.
Okay, maybe a similar question. You have, of course, gauge asymmetry supergravity in which you have a charge, or you have gauge supergravities in which the atoms are charged. You cannot use this to.
People try the supergravity, but the person tried was Dynamical. And then people
the model of Friedman 7%. Gauge asymmetry, for example.
Yeah, the model of Friedman, the mass of the gravitino is related to the cosmological constant. Right. So that's problematic.
So you're in flat space?
And, yeah, I'm doing flat space. And if you then you can try to go to more flat space. Go to flat space by so you break supersymmetry, then the gravitino you have some direct gravitino which is charged. But the mass has to be proportional to Planck. It's E times Planck. So then you have two problems with this theory. It's not Lagrangian is not quadratic; it's quartic. So the equation of motion is not linear. The second problem is that the G, the pure magnetic ratio, when you do minimal coupling, when you add this term, so it will always be 1 over the speed, which is in this case third. Why you want to have 2? So then you don't have unitarity, and then you need to introduce the gravity. So yeah, but I mean, if you want to describe like omega minus, you don't want to
resolve the gravity.
Okay.
If there are no other questions, thanks again. And Asyntonic has something to tell us about the quantum. Thanks.
So just a reminder again that the banquet will start at 6 p.m. at the Surly Brewing. So if you walk from the Graduate, it's 30 minutes. So obviously you're free to walk. If you need help walking, there'll be a local contingent that will be leaving around 5:30. They will either escort you there or they'll take you on the light rail. And then finally, if you have mobility issues or you want a car ride, there'll be 3 cars going